Hello dear students, I am Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to cover the full alcohol, phenol and ether chapter. Now, see, the thing is, when we talk about, when we discuss, when we learn this chapter, most of the time what we do, we focus on the alcohol part, but most of the time we ignore either the phenol part or the ether part, right? So what I have done in this video, I have separated these three. Right? In this session, how you will be studying all these topics, like first you will talk about alcohol completely, its preparations, its properties. Then I will go into phenol, right? And for phenol, I will discuss its preparation methods and its chemical reactions. And then separately, I will talk about ether, that how you can prepare ether and how and what are the chemical reactions we have for ether. Now, you know very well that in the NEET examination, from this particular chapter, we get at least 3 questions in the examination. So those 3 questions you will be able to do easily after watching this session completely. Also, after watching this session, what you will have to do, you will have to solve lots of questions, right? And for that, we are providing DPPs in the video description. And those DPPs, of course, you can get on the PW app. So download the PW app, and just like many students, you also start your NEET journey with us. So let's start, students, today's session with the very first thing, and that will be what are the topics that we are going to cover in this session. So we will start with classification of alcohol and some of the common names, right? Classification and some of the common names of alcohols, because some common names you need to remember, right, for your examination. Then we will talk about how we do the preparations of alcohol and what are the properties like physical and chemical properties of alcohol. After alcohol, we will move into, as I told you, the preparation and the properties or reactions of phenol. So first we will go into alcohol part, and after alcohol we will go into the phenol part, right? And after phenol, we will go into the ether part, and in ether also I will be discussing about how we can prepare ether and what are the properties and reactions of ether we have, right? And at the end, we will see some of the very common alcohols, right, and their uses like methanol and ethanol, right? So starting with the very first thing, that is classification. So if you try to classify alcohol, just like your alkyl halide, it can be classified on number of ways. Like first, if you classify alcohol on the basis of how many hydroxyl group, how many OH group you have in your alcohol. So it can be like monohydric means that alcohol which has only one hydroxyl, one OH group, like this methanol, right? Then it can be dihydric. I think it is self-explanatory. You can understand by the name itself what is the meaning of dihydric, right? An alcohol which has at least 2 hydroxyl group, 2 OH groups, like this. Ethylene glycol, CH2OH, CH2OH. Right? And then you can have a trihydric or polyhydric alcohol. Trihydric means, I hope you know, tri means 3, hydric means a number of hydroxyl group. So trihydric will be that one which have 3 hydroxyl or 3 OH group, like this. CH2OH, CHOH. This is also called as glycerol. So it can be classified, first of all, on the basis of how many hydroxyl or how many OH group you have in your alcohol, right? Monohydric means 1 OH, dihydric means 2 OH, and trihydric means 3 OH, right? After this, the next classification is based on the degree of the alpha carbon, right? Alpha carbon means the carbon by which your OH group, hydroxyl group is attached. So on the basis of degree, alcohol can be classified into 3 parts. We can have primary alcohol, which is also called as 1 degree alcohol. After primary alcohol, we can have secondary alcohol, also 2 degree alcohol. And then we can have a tertiary alcohol or 3 degree alcohol. See, primary alcohol means, or 1 degree alcohol means, alcohol in which the carbon which is attached with hydroxyl group, with this carbon, or we can also say this is alpha carbon. So with this carbon, with this alpha carbon, if only one more carbon is attached and rest 2 are hydrogen, right? So if this alpha carbon is attached with one more carbon, right, then it is called 1 degree carbon, 1 degree alpha carbon, and in that case, it is known as primary alcohol. Similarly, in your secondary alcohol, what will happen? You have this carbon by which your OH group is attached, right, or your alpha carbon. But in secondary alcohol, with your alpha carbon, at least 2 carbon will be attached. So from two sides, we have carbon here and one will be hydrogen. So with your alpha carbon, if two carbons are attached, two different carbons are attached, then it is called 2 degree. And this alcohol is called as secondary or 2 degree alcohol. So I think by knowing primary and secondary alcohol, now you can guess by yourself what is the meaning of tertiary or 3 degree alcohol. Tertiary alcohol, students, is that one in which the carbon by which your hydroxyl group is attached, by which your OH group is attached, or your alpha carbon, it is attached with 3 carbons. So if your alpha carbon is attached with 3 carbons, then this alpha carbon is 3 degree, and then this alcohol will be called as tertiary or 3 degree alcohol, right? So tertiary alcohol is that one in which the carbon by which your OH group is attached or your alpha carbon is attached with 3 carbons. Secondary means the alpha carbon is attached with 2 carbon, and primary means when your alpha carbon is attached with only 1 carbon. And suppose if your alpha carbon is attached only with hydrogen, like in case of methanol, then you cannot you can call it 0 degree alcohol, right? So on the basis of degree of carbon, more precisely we should say on the basis of degree of your alpha carbon, right? On the basis of degree of your alpha carbon, we have a primary, secondary, and tertiary alcohol. Okay, why this point is important? Because later on you are going to see some of the tests that will distinguish between primary, secondary, and tertiary alcohol. So you should have a better understanding regarding what is the meaning of primary, what is the meaning of secondary, and what is the meaning of tertiary alcohol. Now, after this classification, we have one more classification that is on the basis of hybridization, and this classification you must have seen even in your alkyl halide chapter. If you remember, in your alkyl halide chapter, you have something like alkyl halide, aryl halide, vinyl halide, allyl halide, benzyl halide. Same type of classification we have also for alcohol, right? When you say benzyl alcohol, when you say benzyl alcohol, when you say benzyl alcohol. So benzyl alcohol is the one in which you have carbon with which OH group is attached, or your alpha carbon, but with your alpha carbon you have a phenyl group, you have a benzene group. So this is called benzyl alcohol. And if you notice, in this benzyl alcohol, the alpha carbon is sp3 hybridized. Then you have allyl alcohol. Allyl alcohol is the one in which again the alpha carbon is sp3 hybridized. The alpha carbon is sp3 hybridized. But in this case, the beta carbon will be sp2 hybridized. The beta carbon will be sp2 hybridized. So this is your allyl alcohol, right? And the simple one is called as alkyl alcohol, in which you have a simple carbon chain, right? The carbons are sp3 hybridized, and you have a OH group on the alpha carbon, right? But you should have understanding, because sometimes in your questions also, people will directly ask, right? Directly write benzyl alcohol in the question, in the statement. They will directly write allyl alcohol. So you need to understand what is the meaning of benzyl alcohol, allyl alcohol. Similarly, one more we have, which is called vinyl alcohol. See, in case of vinyl alcohol, right, the OH group will be directly attached with the sp2 carbon. Or in that case, in case of vinyl alcohol, your alpha carbon is directly sp2 hybridized. So this is your vinyl alcohol, CH2 double bond CH OH. Right? In this case, the alpha carbon itself is sp2 hybridized. And then if you talk about aryl alcohol, so in your aryl alcohols example, you can have your phenol. You can have your phenol. So phenol is one of the example of aryl alcohol. So you should have a clarification regarding these things, like what is benzyl alcohol, what is allyl alcohol, what is vinyl alcohol, and what is aryl alcohol or phenol. Now, after these classifications, we also have to focus on some of the common names, right? Which is very frequently used in the examinations, in the questions again. Like you should have the knowledge of what is isopropyl alcohol. See, when you say isopropyl, so propyl means you have 3 carbon, total 3 carbon in your chain, and iso means, right, branching on the second last carbon, right? So if you look carefully in the structure of isopropyl, so this is the carbon by which OH group is attached, right? Right? So these 2 carbons, they are continuous, 1, 2. But this is the branch. This is the branch for us on the second last carbon. Because I have only 2 carbon here, 1, 2. So this I can say is the second last carbon. So on your second last carbon, if you have CH3 branch, then it is named as iso. You must have seen that this naming of iso neo in your alkanes isomerism, chain isomerism, normal iso neo. So when you say normal, that means all the carbon chains they are in a straight line, they are continuous, right? And when you say iso, that means you have one methyl group branched on the second last carbon. When you say neo, so that means 2 methyl groups, right? They are branched on the second last carbon, right? Similarly, if you talk about this isobutyl, so in this isobutyl, if you notice, butyl means we should have total of 4 carbon, right? So 1, 2, 3, 4, 4 carbon, and this is the carbon from which OH is attached. So if I do a numbering like this, 1, 2, 3, so I can see here that 3 carbon, they are continuous, but this carbon is branched on the second last carbon again. So if you have a branch on second last carbon, CH3 branch, then it is named as iso. This is isobutyl because total 4 carbon. This is isopropyl because total 3 carbon. Now, one more is there, secondary butyl. So this secondary, you can understand, you can remember from degree itself, right? Again, butyl means how many carbons? 4. And secondary means what? 2 degree. So here if you notice the structure of secondary butyl alcohol, you will notice total that we have 1, 2, 3, 4. 4 carbon is there, butyl, and OH is attached on that carbon which is 2 degree. Which is 2 degree. So from this 2 degree, you can remember this is secondary butyl alcohol. Similarly, if you notice, in this case, third butyl or tertiary butyl alcohol. So again, butyl means what? Total 4 carbon. So we have 1, 2, 3, 4. 4 carbon is there. And third means what? 3 degree. So in third butyl, what's the point? Point is the OH group is attached with that carbon which is 3 degree, right? So when your OH is attached with 2 degree carbon, it is called secondary butyl alcohol. And when your OH is attached with 3 degree carbon, we are calling it tertiary butyl alcohol. Here butyl means total 4 carbon, and here also butyl means total we have 4 carbon, right? So these secondary butyl, tertiary butyl, right? Isopropyl, isobutyl alcohols, right? Their structure you should know, because in so many questions you will see that they will not give you the structure. They will just write down the name, and from name you have to draw the structure. Few more common names we have, like ethylene glycol. I told you already. Ethylene glycol means we have 2 carbon, CH2, CH2, and on those 2 carbon we have 2 OH group. So it is an example of a dihydric alcohol. And similarly, we have glycerol, in which total we have 3 carbon, CH2, CH, CH2. And on each carbon we have OH group. So total we have 3 OH group here. So glycerol is one of the example of trihydric alcohol, right? So after these common names, okay, one thing I hope that you know from your GOC chapter, and that is nomenclature. I hope that for alcohols, you people know very well the IUPAC nomenclature, right? Primary suffix, secondary suffix, and for alcohol, the secondary suffix you write is or, right? So IUPAC nomenclature of this alcohol part you can do from GOC basic organic chemistry videos, right? Now let's move ahead and let's focus on the major part of this chapter from which we get questions most of the time. You also know that very well. That will be preparations and properties. But before that, we have few more common names, like this is from your phenol part, right? Cresol. So cresol is something like this, benzene ring, and it is a di-substituted compound. So one group is methyl and one group is OH. Okay, and when your benzene is di-substituted, you know that you can call it ortho meta para, right? So in this case, methyl group and OH group, they are present on adjacent position. So this is nothing but orthocresol. This is nothing but orthocresol. And if you put it on 1,3 position, like CH3 here, OH here, then that will be called as metacresol, right? If you put that on 1,4 position, like methyl here and OH here, then that will be called as paracresol. But overall, cresol means you need to understand that we have a di-substituted benzene, right, in which one group is methyl and one group is OH. Similarly, if you talk about catechol, resorcinol, and hydroquinone, right, so these are also di-substituted benzene, but in this case, we have two OH groups only, no methyl group, right? So catechol is something like this, two OH groups on the ortho position. Resorcinol is two OH groups on the meta position, and hydroquinone means two OH groups on the para position. So again, these are also common names, but they are from the phenol part, right? So now let's move on to, after this some common names part, let's move on to the preparation part of alcohol, right? Yeah. And again, let me tell you one thing. I have told this point, this part in your Hello Alkanes video, that in your organic, you always synthesize, you prepare an organic compound from other organic compounds. So if you talk about alcohol, so the major preparations of alcohol we do from either alkene, right, or aldehyde ketone or acid. So alkene, aldehyde ketone and acid, these three are the compounds from which mainly you prepare your alcohol. And out of these three also, the most important one is alkene, right? So for alcohol, preparation of alcohol from alkene is the important point. And the first preparation we have of alcohol is from alkene only, but the method is acid catalyzed hydration, right? I hope this reaction you also had seen, right, in your hydrocarbons chapter. Right, in your hydrocarbon, when you talk about reactions of alkene, remember that Markovnikov additions and all. So during the reactions of alkene also, you discuss this reaction. Overall, what it says, that if you take an alkane, not alkane, of course, alkene. If you take an alkene, right, I have taken unsymmetrical alkene so that we can understand Markovnikov rule here. So if I take unsymmetrical alkene and I do hydration here, with water and dilute acid like dilute H2SO4. So what will happen? Water will be added overall like this: CH3, CH, OH, CH2H. So point is, from this water, from this reagent, H plus is getting attached on this carbon, on first carbon, and the nucleophile OH minus, it is getting attached on the second carbon, right? And that's what Markovnikov rule says. Markovnikov rule says that during addition on alkene, electrophile will be added on that carbon which has more hydrogen, and nucleophile will be added on that carbon which has less hydrogen. So on first carbon we have two hydrogen, so that's why I added electrophile on the first carbon, and on the second carbon we have only one hydrogen, so I added nucleophile on the second carbon. So overall, in this case, the product you get is Markovnikov product. But if you talk about the mechanism of this reaction, how it happens, because mechanisms are always important in the organic chemistry. So if you talk about the mechanism, so in very first step here, with your alkene, the electrophile will be added, because you know very well now, I hope you feel very well now, that alkene functions like a nucleophile. Alkenes have always tendency to share its pi bond, and with whom it will share its pi bond? Of course, with electrophile. So in this H2OH plus, if you notice, the electrophile part is H plus. So in the very first step, it will share its pi bond with H plus ion, right? Creating an stable carbocation. So in this case, the stable carbocation will be this. I think you know very well. If I add H plus on first carbon, so carbocation will be created here, which is a 2-degree carbocation, it will have total 3 and 3, 6 hyperconjugates. And if I add H plus here, because that is also possible, so in that case, carbocation will be created here, which is 1 degree, and it will have only 2 hyperconjugates. So definitely, this carbocation and one more, this one, these two can be formed. But very easily we can say that this is the more stable carbocation. And more stable carbocation here will further proceed, will give you the major product. But please notice one thing here. Because during the acid catalyzed hydration of alkene, we are getting carbocation intermediate. So again, students, rearrangements are possible here. You can have a hydride shift, methyl shift, ring expansion, all those shiftings are possible in this reaction. So whenever you are solving a question from this reaction, right? So do the mechanism, create the carbocation, right? Wait for a few seconds, check for the rearrangement, whether rearrangement is possible or not, right? That can be checked very easily by looking like whether your carbocation can become more stable on adjacent carbon or not. Like in this case, we are getting this as a more stable carbocation, right? So if I shift this positive charge on the right carbon or left carbon, the stability will decrease. So if stability is decreasing, right, that means no rearrangement is possible in this case, right? But if possible, in some cases you can have rearrangement here. So please be careful and be careful in that. Now in this case, what will happen? In the second step, water as a nucleophile, it will attack on the carbocation, and later on from this H2O molecule, one H plus will remove. That means deprotonation. So overall, the mechanism of this reaction we can write in 3 steps. First, electrophile attack or formation of carbocation. Second, attack of nucleophile, right? And third, the deprotonation of H plus from this H2O part. But finally, you will get this Markovnikov product, right? So you need to understand that we are getting Markovnikov product. But if in case rearrangement will happen, then that Markovnikov rule will not be applicable here. One more point, we have taken unsymmetrical alkene. Anytime if you take symmetrical alkene, so in case of symmetrical alkene also, your Markovnikov rule will not be applicable. So in those cases, at the end, you have to follow the mechanism. You have to follow the mechanism, right? So now I think you have understood very well that how we get alcohol by the acid catalyzed hydration of alkene. Let me take one more example. So if I take this as your substrate, and for this substrate, of course, it's a cycloalkene, but we have double bond in it. That's the main point. And if I ask, what will be the major product after hydration of this substrate, right? So you can try by your own first. You can pause the video, you can get your answer, and later on you can confirm with me, right? But the point is, as you know very well that alkene loves electrophile, right? Alkene has a very much love towards your electrophile. And during the hydration, of course, our electrophile is nothing but proton, that means H plus. And your substrate is this. Your substrate is this. So what this alkene will do, it will share its pi bond, it will share its pi electrons with your electrophile, that means H plus, right? So I can say like this, that initially here in the first step, this pi bond will be shared by this H plus, this electrophile, and again we have 2 probabilities, like first this H plus can be added here on this carbon. In that case, your carbocation will look like this. If you add H plus on this carbon, then carbocation will be created here, right? And the other probability is, if your H plus is getting added on this carbon, right, then on the other carbon, again you will be getting a carbocation. So in this time, when your H plus is getting added here on this carbon, so carbocation will be created on this carbon, right? So these 2 possible carbocation we can get in this reaction. Now, you know very well that in a reaction when you get carbocation as intermediate, so you need to check up the stability of carbocation, and the more stable carbocation will give you the major product. Now here, if you notice carefully, this is a 3-degree carbocation, this is a 2-degree carbocation. This carbocation has 3, 2, 2 total 3 hyperconjugates from this, 2 hyperconjugates from this, and 2 hyperconjugates from this. So 3 plus 2 plus 2, this carbocation has a total of 7 hyperconjugates. But this carbocation, it has 1 hyperconjugates from here and 2 from here. So this carbocation has only 3 hyperconjugates. So definitely this carbocation is more stable, right? So in the next step, this carbocation will give you the major product, and you know very well, I told you in the next step, your nucleophile H2O, right? It will attack to make the carbocation stable. Then you will get this sort of structure, O, H, H, and now because your oxygen is sharing its lone pair with coordinate bond, so definitely it will get some formal charge that will be +1. So this oxygen now it has a +1 charge with one lone pair, and ultimately the third step we had was deprotonation, right? So here in the deprotonation step, again this OH bond will break, oxygen will take back its electron, right, and one H plus will be removed, and students, your major product here in this case will be this one, right? The carbon where you have a methyl group, on the same carbon you will have your OH group, right? But your minor product in this case will be when your nucleophile attacks on this carbocation, and that will be something like this, right? So we can get two products here, but of course the first one is the major and the second one is the minor. So I think automatically you have understood, students, that in this reaction during the direct hydration of alkene, right, if you have to decide which one is your major product, so that you can decide with the stability of carbocation, right? More stable carbocation will give you the major product, right? But of course it is the first method of preparation of alcohol for us. But again, if I talk about this reaction, so this reaction you discuss at least in 2 chapters, right? One is hydrocarbon and the other one is alcohol, right? Now with this, let's move on to the next preparation of alcohol, students, and it is again from alkene, right? I told you that alkene is the important part here, right? Preparation of alcohol from alkene is the main part here, right? So the second preparation again we have from alkene, but this time instead of doing direct hydration or acid catalyzed hydration, what we are gonna do, we're gonna do hydroboration-oxidation. Now before I begin in this reaction, before I start explaining this reaction, let me tell you a few points here, right? In the hydroboration-oxidation alkene, the major difference from this from that acid catalyzed hydration is, in this reaction your product will be according to anti-Markovnikov addition. Your product will be according to anti-Markovnikov addition. And one more point, in this reaction we do not get any carbocation intermediate, so in this case rearrangements are not possible. These are some features you can say for this hydroboration-oxidation. Features like no rearrangement possible in this, right? The final product we get is according to anti-Markovnikov addition, right? And one more point is there, that is if you talk about the stereochemistry of this reaction, so it is a kind of syn addition, means your electrophiles and nucleophile, right, they will be added on the same side of the carbon. They will be always on the same side of certain plane. So that's why we call it is a syn addition reaction. Now, first of all, let's take an example to understand this reaction. Like let's take an alkene. Again, it's better to always take unsymmetrical alkene, because in symmetrical alkene, deciding product is very easy for you, right? So if I take my favorite, propene, right? And for this propene, I do hydroboration. So point is, hydroboration is done by treating your alkene with boron hydride B2H6, right? And this is the first step when you treat this B2H6, right, with your alkene. And sometimes you will notice that along with B2H6 you have THF, tetrahydrofuran. So that THF is basically used to break the dimer, right? B2H6 is a dimer and its monomer is BH3, right? So to convert B2H6 into BH3, we use this THF. So in first step, we treat alkene with B2H6 THF, and then in the second step, right, we do oxidation by H2O2. That means peroxide. And here, if I talk about the final product, so if you remember, what is Markovnikov rule? Markovnikov rule says that electrophile should be added on this carbon where we have more hydrogen, and nucleophile should be added on this carbon where we have less hydrogen. Now in this case, the final product we get is according to anti-Markovnikov addition. So in this case, what will happen? The electrophile will be added here on that carbon which has, no, electrophile will not be added here. Electrophile will be added here, that carbon which has less number of hydrogen. That is anti-Markovnikov rule. And nucleophile in this case will be added here on this carbon which has more hydrogen. So I can directly write the product. I can directly write the product like this. The product will be CS3, CH2, CH2OH. Now, instead of hydroboration-oxidation, in this case, if you do direct hydration, right? So in the direct hydration, you get Markovnikov product. In that case, in direct hydration, the OH will be added on this carbon, right? But in this case, because we are having anti-Markovnikov product, so OH is added on this carbon which has, you can say, more number of hydrogen or lower degree of carbon. Now, if I talk about the mechanism of this reaction, of course, mechanisms are always important, because you know what? You can forget the product, but you can never forget the mechanism. So always focus on the mechanism part, students, because mechanism will make your organic chemistry stronger, right? So in this case, our substrate is alkene, which is CS3, CH, double bond, CH2. And our reagent is, right, boron hydride, that means BH3. Now, if you notice carefully, in your BH3, the boron atom is octet deficient. So in your BH3, the boron atom will act as electrophile, right? And from BH3, we get one H minus, so that H minus here acts as nucleophile. But the main thing is, although we get the product according to anti-Markovnikov rule, the final product we get is according to anti-Markovnikov product, right? But the mechanism is still Markovnikov addition. If you follow the mechanism, so its mechanism is again according to Markovnikov rule, right? Because in the very first step, this boron electrophile, it will be added on this carbon, which has more hydrogen, and this hydride will be added on this carbon, which has less hydrogen. So this is Markovnikov rule, right? Electrophile on lower degree carbon and nucleophile on higher degree carbon. And here we get this kind of intermediate, a cyclic ring, a cyclic 4-membered ring. 2 carbon, 1 boron, 1 hydrogen. We do not get any carbocation here, right? And ultimately, this BH bond will break, this pi bond will break, and your product will be CS3, CH, H, CH2 and BH2, right? And why this reaction is called hydroboration? Because it's very much logical. If you notice, in your alkene, on this carbon, boron has been added, and on this carbon, hydrogen has been added. So because hydrogen and boron atoms are getting added in your substrate, so it is called as hydroboration. And this step is according to Markovnikov rule. Boron electrophile part, hydride nucleophile part, boron is getting added on lower degree carbon which has more hydrogen, and hydride is added on that carbon which has less hydrogen. So the addition is according to Markovnikov rule. But point is, the final product we get, that means this one, that product looks like anti-Markovnikov. So we say that the addition is Markovnikov, right? The addition follows Markovnikov rule, but the final product we get is anti-Markovnikov product. We never say that here anti-Markovnikov rule is getting followed. We say that our product is anti-Markovnikov, correct? Now, in the second step here, right, after addition of hydrogen boron, in the second step, when you do oxidation with H2O2, you know that H2O2 can break from this oxygen-oxygen bond. So that H2O2 will oxidize this carbon-boron bond, right? From this H2O2, one OH will be added on this carbon, one OH will be added on this boron, you will get this product, right? And sometimes you will notice that instead of one time, right, you will have 3-time reaction. 3-time means because that boron still has 2 hydrogen, so 2 more alkenes can be added here. So do not get confused by that, right? I have taken just 1:1 ratio, 1 alkene with 1 BS3, and sometimes you can find a 3:1 ratio, right? 3 alkene reacting with 1 BS3. But in both the time, right, your final product will be this. Now, in the very first step itself, if you notice, so in this BS3, because the boron and hydrogen, they are getting added simultaneously together, so they will be added from the same side. They will be added from the same side. So that's why we say that this is one of the example of syn addition. Syn addition. Right? And you can also notice that we are not getting a carbocation intermediate here. Instead of that, we are getting a cyclic intermediate. So because we are not getting a carbocation, so in this case, no rearrangement is possible. No rearrangement is possible. Right? And overall, the mechanism follows Markovnikov rule. But the final product we get, that looks like anti-Markovnikov product. That looks like anti-Markovnikov's product. So these 2-3 points you need to always keep in your mind regarding your hydroboration-oxidation reaction. Right? Now, apart from this hydroboration-oxidation of alkene, by which you get, of course, you can say lower degree alkene. Lower degree alcohol. You can remember like this. Like when you do direct hydration, so from that you can obtain higher degree alcohol. And when you do hydroboration-oxidation, so from that you can obtain lower degree alcohol. Right? This time we got 1 degree or primary alcohol. With the same alkene, when I was doing direct hydration, if you remember, right? With the same alkene, when I was doing direct hydration, so I was getting 2 degree alcohol. Right? So like this also you can remember that direct hydration of alkene can give you higher degree alcohol, and hydroboration-oxidation, right, of alkene can give you lower degree of alcohol. Right? Now, with this, let me discuss one more. So, along with hydroboration-oxidation, one more method I think you should know, that is oxymercuration, and demercuration. Oxymercuration and demercuration. Now, in oxymercuration, demercuration, what's the point? The product you will be getting, right, that will look like according to Markovnikov rule itself, but in this case again, you won't have any kind of rearrangement, right? So point is, if you want to prepare a higher degree alcohol, if you want to get alcohol according to the anti-Markovnikov product, but you don't want any kind of rearrangement, then you can use this oxymercuration-demercuration instead of direct hydration of alkene. Now, in oxymercuration-demercuration, what we do, we take our alkene, and we treat that with mercuric acetate first. We treat that with mercuric acetate first. Here AC means, you know, acetyl group, CH3CO. Right? When you treat with mercuric acetate, just like hydroboration, like in your hydroboration, on this carbon, boron was getting added, on this carbon, hydrogen was getting added. So in this case, on this carbon, your mercury will be added, right? And you will be getting a cyclic kind of intermediate here. CH3CH2, Hg, right? OAC. HgOAC. Right? And if I use water as a nucleophile here, right? So later on this cyclic intermediate, the H2O nucleophile will attack. Again, you know that when H2O will attack, there will be a deprotonation. So finally, you will have OH group here on this carbon. And by the attack of H2O nucleophile, this cyclic intermediate will decompose, and your product will look like this. CH3, CH, OH, CH2, and HgOAC, right? And finally, if you want to remove this mercury, so you need to do reduction here by the suitable reducing agent, which can be NaBH4 in this case, right? So when you use NaBH4 here, right, so that NaBH4 will reduce the carbon mercury bond, right? NaBH4 can give H plus H minus, right? So that H plus can attach with carbon, because carbon has delta negative charge, and H minus can attach here, right? And ultimately, after reduction of that carbon mercury bond, your product will be CS3, CH, OH and CS3. So one more method, this we have for the preparation of alcohol along with direct hydration and hydroboration. It is called as oxymercuration-demercuration. Now the main thing is, if you compare all these three, because these three I think you should remember together. If you compare all these three, like direct hydration, hydroboration and oxymercuration-demercuration. So point is, in case of direct hydration and oxymercuration-demercuration, you get Markovnikov product. And in case of hydroboration-oxidation, you get anti-Markovnikov product, right? But the major difference is in rearrangement, right? In case of direct hydration, you can have rearrangement because we get carbocation intermediate. But in both hydroboration and oxymercuration-demercuration, you don't get any kind of rearrangement. One more point I would like to tell here, that because I wanted to prepare alcohol, I used H2O as a nucleophile. In this reaction, instead of H2O, I can use different nucleophiles too. So whatever nucleophile I use, that will attack on this carbon to break this cyclic intermediate, right? So I think now collectively you will remember these three methods of preparation of alcohol from alkene, right? Direct hydration or acid catalyzed hydration, hydroboration oxidation and oxymercuration-demercuration. From these three methods of preparation of alcohol from alkene, you get questions in your examination. So now after alkene, let's talk about the next aldehyde ketone, right? And how we obtain alcohol from aldehyde ketone. So basically from aldehyde ketone, there are two ways by which you can get your alcohol. One is by reduction, and later on you are going to see the other method is using Grignard reagent with your aldehyde ketone. But first let's talk about how we can obtain alcohol by the reduction, or you can say partial reduction of aldehyde ketone. I hope you all know very well that when I say aldehyde, so that basically means R, C double bond OH. R can be your alkyl group, it can be open chain, it can be cyclic, right? And ketone also you know very well, RC double bond OR dash, right? And along with aldehyde ketone, I can also use acid, right, to produce alcohol. So acid, you know that you can have a open chain or cyclic ring alkyl group, right? RC double bond OOH. Now, to convert aldehyde ketone or acid into alcohol, the most suitable reagent is lithium aluminium hydride, which is also known as written as LAH, right? And NaBH4, sodium borohydride. So these two can be used to convert aldehyde ketone acid into alcohol. Or you can remember like this. Here, forget about the preparation of alcohol. You just focus on this reagent, students. You need to understand this LiAlH4, NaBH4. And you can remember this like LiAlH4, NaBH4, they reduce the pi bond. But mostly hetero-pi bond. Hetero-pi bond means when your pi bond is present between two different atoms. So point is, your LiAlH4, NaBH4 will not reduce, right, the carbon-carbon pi bond. Like if you take alkene, like this, right? So if you have a pi bond between carbon atom, so this pi bond cannot be reduced by your LiAlH4, NaBH4. But whenever you have hetero-pi bonds like a pi bond between carbon-oxygen atom, pi bond between carbon-nitrogen atom, so those hetero-pi bonds can be reduced by your LiAlH4, NaBH4. Now in this case, when I talk about aldehyde, right? So in aldehyde, we have a pi bond here between carbon-oxygen. So of course, it's a hetero-pi bond. Pi bond between carbon-oxygen means pi bond between two different atoms. So that pi bond can be reduced by both LiAlH4 and NaBH4. Both can be used here. And what it will do, it will break your pi bond, it will add one hydrogen here, one hydrogen here, and your product will be RCH HOH. Right? Similarly, if you talk about ketone, so in ketone also, I can use LiAlH4, NaBH4 both, right? And again in ketone, you can notice that between your carbon oxygen in your carbonyl, you have a hetero pi bond. Pi bond means, hetero pi bond means again pi bond between two different atoms, carbon and oxygen. So again that hetero pi bond can be reduced by your LiLH4 NaBH4. And how it will be reduced? The pi bond will break and hydrogens will be added on your carbon and oxygen atoms. Now, if you notice carefully, by the partial reduction of aldehyde, we are getting 1 degree or primary alcohol. But by the reduction of ketone, we are getting 2 degree or secondary alcohol, right? And at the same time, if you try to reduce your carboxylic acid group, right? So by the reduction of carboxylic acid group, by the reduction of this carbon, again you will be getting primary alcohol only. But please remember one thing. When you are reducing carboxylic acid, you can use only lithium aluminium hydride. Because NaBH4, it is weaker than LiLH4. So NaBH4 will not reduce your carboxylic acid. So for aldehyde ketone, both LiLH4 and NaBH4 can be used. But for carboxylic acid, you can use only LiLH4. NaBH4 will not reduce carboxylic acid or its derivative. Right? Out of the derivatives, there is only one compound, that is acid chloride. Only this acid chloride can be reduced by your NaBH4. Only acid chloride can be reduced by NaBH4. Apart from acid chloride, whatever acid or acid derivative you have, acid derivative means ester, amide, right? So those acid derivatives or acid, they are not reduced by NaBH4, right? So remember like this, focus on this LiLH4 or NaBH4, right? It can reduce hetero pi bonds, right? It can convert aldehyde ketone acid into alcohol, but it cannot reduce carbon-carbon pi bond, right? But there is a case, right? If you can memorize that, it will be very much better for you. There is a case in which the carbon-carbon pi bond can be reduced by LiAlH4, not by NaBH4, only by LiAlH4. Suppose if you see this kind of structure, you have a benzene and with your benzene, a CC double bond is attached, and suppose you have a carbonyl group here like aldehyde or ketone. So in this case, if I use LiAlH4, so of course this aldehyde part will oxidize into alcohol, 1 degree alcohol, and here the carbon-carbon double bond, it will be also reduced, right? And you will be getting CH2 single bond CH2. So only when you have a CC double bond, right, in conjugation with your benzene, right? So that CC double bond can be reduced by LiAlH4. Again, NaBH4 is weaker, so NaBH4 will not reduce this CC double bond. So these many points you need to remember regarding your LiAlH4 NaBH4. Although no doubt we are discussing the preparation of alcohol, right? Preparation of alcohol from aldehyde ketone. And that's why we have talked about these two reagents. But here, apart from preparation, you need to think like this, that these reagents are important for us. And in your organic chemistry, you should make a list of all your reagents. Please do that, because that will make your revision very much easier. For all those chapters like hydrocarbons, haloalkanes, haloarenes, alcohol, phenol, ether, aldehyde, ketone, acid, amine, right? For all those chapters, in every reaction, whatever reagents you have, write down those reagents on a paper, right? Write down their functions. It will take hardly 2-3 pages, and time to time you can revise that, and your organic will become much simpler to you. So after reduction of aldehyde ketone acid into alcohol, right? Now the next preparation we have for alcohol is again from aldehyde ketone. But this time, instead of doing reduction, we are going to use Grignard reagent. I hope you know Grignard reagent very well, that the structure of Grignard reagent can be given as RMgX, in which R is alkyl group and R always carries partial negative charge. And X can be your halogen, and this magnesium atom this always carries some partial positive charge. And please students always remember that whenever you have a Grignard reagent in your reactions, right, so it will break into R minus Mg plus. Sometimes you can say that RMGX acts as a nucleophile because RMGX can give you R minus. R minus is a nucleophile. Now point is, if I take a aldehyde, like this, R dash C double bond OH, right? And I treat with some Grignard reagent here, in general RMGX, right? So point is, RMGX can give you R minus, and you know, carbonyls, they are very much able to add nucleophiles. Students, in this session only, I told you that alkenes, they love electrophile. Similarly, you can remember like this, that carbonyls, they love nucleophile. Why? Because in carbonyl, this carbon has some delta positive charge, right? So this carbon will attract nucleophile easily. So as soon as you treat your aldehyde or ketone with Grignard reagent, right, this R minus nucleophile will attack on this carbon. Now to maintain the valency, this pi bond will shift into oxygen, and that O minus will grab this Mg plus ion, and you will be getting an addition product like this, R dash C H OMG X, and on this carbon you have another alkyl group, right? And whenever you have metal with oxygen, so that metal can be simply removed by protonation. So if you do protonation here, that Mg part will be removed, and your final product will be R dash CH R OH. Right? And if you focus from aldehyde using Grignard, I am getting alcohol, and that alcohol is 2 degree or secondary alcohol. Similarly, if I use ketone instead of aldehyde, just for difference, I am taking different alkyl groups here. R dash means something like methyl, ethyl, propyl, butyl, anything, or it can be cyclic ring also. So two different alkyl groups we have, that means we have an unsymmetrical ketone, and if I treat that with some Grignard reagent, again same mechanism will happen. This R minus will attack on this carbon, pi bond will shift on oxygen, oxygen will grab the Mg plus ion to maintain neutrality. You will get addition product like this, R dash C R double dash O MgX and R. And again, if you do protonation, you will get your alcohol, which will look like R dash C R R double dash OH. And in this case, if you notice, you are getting 3 degree alcohol. So point is, when I use Grignard reagent, so from aldehyde, I will be getting 2 degree alcohol, and from ketone, I will be getting 3 degree alcohol. But if I want to get primary alcohol here, I can use formaldehyde. Using formaldehyde, I can obtain primary alcohol in this. And again, the mechanism will be same. So although we are talking about preparation of alcohol here, but if you remember, these reactions are there in your aldehyde ketone chapter too. In your aldehyde ketone chapter, you have a topic called nucleophilic addition reaction, right? So in your nucleophilic addition reaction, you talk about addition of Grignard reagent on your aldehyde and ketone, right? But point is, whenever we do addition of Grignard reagent on aldehyde ketone, we get finally alcohol. We get finally what? Alcohol. So that's why we are talking about this in the preparation of alcohol, right? So point is, now we have done all the preparations of alcohol that we have in our syllabus, right? Preparation of alcohol from alkene. From alkene, it's very important because from alkene we have 3 methods: direct hydration, hydroboration, oxymercuration, demercuration, right? Then by the reduction of aldehyde ketone using LiLH4, NaBH4 or acid, right? And then by addition of Grignard reagent using aldehyde ketone, right? One more method of preparation of aldehyde alcohol you can say here, that is by hydrolysis of alkyl halide. But I think that reaction is very much simple to you. Like when you take alkyl halide, you do SN2 reaction, you treat with aqueous NaOH, aqueous KOH, you get your alcohol. So that method of preparation can be there for alcohol. Now, point is, after preparation, we talk about chemical reactions. But here, before we move into the chemical reaction part, we have to focus on some of the physical properties too, right? Like this is one of the ignored part, you can say, we have. Many people, they do not focus on the bond angle, right? In this chapter, bond angle is a major topic and you can get question from this. Point is, when you talk about alcohol, phenol and ether, all these three we have to discuss in this chapter. But if you focus on the bond angle, right? So hybridization of the central atom in each case, right? It is nothing but sp3, because whether it is alcohol, phenol or ether, every time your central atom is oxygen. So according to geometry, right? According to hybridization, if you judge, it should be 109 degree 28 minutes, right? According to the chemical bonding chapter, if you know. So the perfect angle here should be 109 degree 28 minutes. But of course it will deviate because we have lone pair on the oxygen atom, right? So in case of normal alcohol, it is nearly 108.9 degree. In case of phenol, it is 109 degree. And in case of ether, it is 111.7 degree. Now from here, we can get reasoning questions. What type of reasoning questions? Of course, in each case, the angle is deviating from 109 degree 28 minute. But if you compare, instead of alcohol, your phenol has a little bit of higher angle. Now they can ask what can be the probable reason behind that. So reason is very simple. The resonance of this lone pair with your benzene. You know that whenever you have a delocalized lone pair, right? So that delocalized lone pair can increase the bond angle. So because in phenol we have resonance of this lone pair of oxygen atom, so that's why it has a little bit of higher bond angle than a normal alcohol. And at the same time, if you talk about your ether, so ether has a higher bond angle than both alcohol phenol. Now what can be the reason behind that? In ether, if you notice, both side we have alkyl group, right? Both side we have a bulkier group. In case of whether it is alcohol or ether, on one side of oxygen we have hydrogen. Hydrogen has a small size, right? So whether it is alcohol or phenol, in both the case, one side we have a hydrogen which has a smaller size. But in case of ether, both side of oxygen we have alkyl group, right? So due to steric repulsion between these two bulky groups, in case of ether we have more bond angle as compared to both alcohol and phenol. So regarding this bond angle, you can definitely get some reasoning questions in your examination. So please keep that in your mind. Now, after bond angle, of course, when we talk about physical properties, so these things are common, like boiling point and solubility. You talk about these two, boiling point and solubility, in each and every chapter of organic chemistry. So here again, if you talk about boiling points of alcohol, so definitely in alcohol you have intermolecular hydrogen bond, right? So if you compare boiling point of alcohol with any organic compound which is not having intermolecular hydrogen bonding of a similar molecular mass, then of course alcohol will have more boiling point due to intermolecular hydrogen bond. And within your alcohol, if you notice, right, so with molar mass, with increase in molar mass, right, your boiling point increases, right? So in the same homologous series, as you have more and more carbon, as your molar mass increases, right, the boiling point will increase. And one thing I think you know from the hydrocarbon chapter itself, that when you have branching, so branching will decrease the boiling point. Branching will decrease the boiling point. And you can say that we have a trick here, right? Whenever people ask that why alcohol has more boiling point than any other compound of same molecular mass, like if you compare alcohol with alkane, alkene, alkyne, alkyl halide, aldehyde, ketone, ether, right? So why alcohol has more boiling point than all those compounds? Because alcohol has intermolecular hydrogen bond. Because alcohol has intermolecular hydrogen bonding, right? So keep that in mind for your reasoning questions, right? And keep these 2 points in your mind for the comparison of boiling point of alcohol, right? Now, apart from boiling point, one more point we have to discuss here regarding the solubility. You know that most of the organic compounds, they are not very much soluble in water, but alcohol is. And I hope you know very well that alcohol is very much soluble in water. Now, why alcohol is very much soluble in water? Because again, the reason is intermolecular hydrogen bonding. The reason is intermolecular hydrogen bonding, right? When you mix alcohol in water, right? So you know that water molecule is this H2O, and alcohol molecule has a similar structure like this. So point is, the hydrogen of alcohol molecule and oxygen of water molecule, they can create hydrogen bonding in between them. Right, so in the mixture of alcohol water, we have intermolecular hydrogen bond between the alcohol molecule and water molecule. And whenever we have bonding between the solute and solvent, right, so they are soluble. So alcohol is pretty much soluble because it can create intermolecular hydrogen bond with water. Right. So now these 3 points like bond angle, solubility, and of course boiling point, because you can get statement based questions from this. Please keep in mind, from these physical properties you can get statement based questions, reasoning questions and all, from bond angle, boiling point and solubility. Now let's go and let's discuss the chemical properties or the chemical reactions of alcohol. And if you talk about alcohol, so let me first tell you one thing. Students, if you notice the structure of alcohol, right, ROH, alkyl group, oxygen atom, hydrogen atom. So we have 2 polar bonds here. One polar bond is carbon oxygen and one polar bond is between oxygen hydrogen. Now during reaction, right, there is a probability that either this bond will break or this bond will break. Now point is, during your reaction, if the OH bond is breaking, if OH bond is having fission, so it will release H plus and your alcohol will show acidic nature there, right? And during reaction, if the RO bond is getting RO bond is having fission, right? So that means in that case, carbocation will be separated and you will be getting OH minus. So if your alcohol is giving OH minus, that means in those reactions, alcohol will act like a base because it is providing OH minus. Now, most of the time, we notice acidic nature of alcohol, and there are certain reactions which can prove it, especially when you react a pure metal with alcohol, right? Like you take sodium, you react sodium with alcohol. What it will do? In this case, this OH bond will break, right? So from here you will be getting H plus, sodium will give you electron, and H plus electron, right, it can create H2 gas, hydrogen gas, and byproduct will be Na will convert into Na plus, and here you will have RO minus. So byproduct will be sodium alkoxide in this case. Not only sodium, you can take other reactive metals too, like magnesium or aluminium, right? If I take magnesium here, so magnesium can react with alcohol, again in the same way, again this OH bond will break, it will give you H plus, means acidic behavior, alcohol is showing here. This H plus magnesium's electron will provide hydrogen gas, and here you will be getting magnesium alkoxide. So reaction of alcohol with metal shows that alcohol can have acidic nature, because similar type of reaction we have, right, for the inorganic acids, right? In your, I think even 10th class, you must have learned that when you take dilute acid and you react that with metal, so dilute acid with metal gives you hydrogen gas plus salt. So just like dilute acid, here alcohol, when it is reacting with reactive metals, it is providing H2 gas. So from this reaction we can say that alcohol has acidic nature. But point is, no doubt alcohol has acidic nature, but please remember that your alcohol under normal condition, it will not show neutralization reaction. If you take alcohol, so it will not react with a base, right? Only one alcohol is there which can react with NaOH, and that is methanol, because methanol is more acidic than water. So only methanol is there which can react with NaOH base to show that neutralization reaction. It can give you CH3ONA plus H2O. But apart from methanol, rest of the alcohol, whether it is ethanol, propanol, butanol, right, they do not react with base like NaOH or KOH. Right? But at least from the reaction of metal alcohol, we can say that alcohol has acidic nature. Now, from this point, we need to discuss one thing, right? Because we do get question from that also. Students, sometimes in your examination, you will be getting questions of comparison of acidic strength of alcohol, right? Which alcohol is more acidic, which alcohol is less acidic. Now, those comparison of acidic strength will be pretty much easier to you. Like the very first comparison of acidic strength is based on degree, right? If you take primary alcohol or 1 degree, and if you take secondary alcohol, that means 2 degree. If you take tertiary alcohol, that means 3 degree. So out of primary, secondary, tertiary, the most acidic one will be primary, then secondary, then tertiary. This is the order of acidic strength according to degree. So according to different parameters you can get. Like this is a comparison based on degree of alcohol. So why this 1 degree alcohol is more acidic than 2 degree, and 2 degree alcohol is more acidic than 3 degree? So that can be explained on the basis of stability of conjugate base. Like if you take primary alcohol like this, CH3, CH2OH, right? And this alcohol, for this if you draw the conjugate base, so it will be CH3, CH2O minus, right? And if you take a 2 degree alcohol like this, CH3, O, CH3. CH3, CH3, H, OH. So if you take 2 degree alcohol, right? So in this case, your conjugate base will be CH3, CH, CH3, O minus. Now if you compare these two bases, right, you can clearly say that this base, this conjugate base is more stable, because in this case we have a plus I effect only from one side, right? But in this case there are two carbons which can show from two sides we have plus I effect. You know that plus I effect decreases the stability of an ion, right? So because here we have more inductive effect, more plus I effect, so 2 degree anion is less stable. 2 degree anion or base of 2 degree alcohol is less stable than the base of 1 degree alcohol, right? Similarly, the conjugate base of 3 degree alcohol will be least stable, because in that case you will have plus I effect from 3 side. So sometimes you get direct question from this comparison of acidic strength on the basis of primary, secondary and tertiary alcohol. And not only that, I think because I talked about inductive effect, so you should know that if your alcohol has minus I effect, or minus I groups are attached in your alcohol, so definitely minus I group, minus I effect will increase the acidic strength, right? And you know that minus I effects are shown by halogen, right? Nitro groups, cyanide, right? Carbonyls. So if you see that in your alcohol, these groups are attached, so that will increase the acidic strength of alcohol. But my point is, of course, the comparison of acidic and basic strength you also discuss in your GOC, basic organic chapter. But from this chapter, right, the comparison of acidic strength of alcohol you can get in your examination. So you need to practice questions from that also. Questions from comparison of acidic strength of alcohol, right? Now, after acidic nature of alcohol, after comparing the acidic strength of alcohol, now let's talk about some more reactions of alcohol, right? And the second one is esterification. I hope esterification reaction you know from your 10th class itself, right? In 10th class you have a chapter called carbon and its compound. In that chapter also you have this reaction esterification. So what's the main point of this esterification is, if you take a carbonyl compound, like carboxylic acid, right? You can also take acid derivatives here, right? Like acid chloride or anhydride. And if you react a carboxylic acid with alcohol, right? So in this reaction, your alcohol will act as a nucleophile. Anyway, you need to remember one thing, that alcohols, if you talk about the feeling of alcohol, so alcohols have always tendency to donate electron from the oxygen atom, right? So in this case, your alcohol will act as a nucleophile. It will attack on this carbonyl, and ultimately, right, this OH part will be removed. So you can say that it is a kind of SN reaction of your carboxylic acid. It's an example of SN reaction of carboxylic acid, where alcohol is acting like a nucleophile. So here this OH nucleophile is getting replaced by this OR dash nucleophile, and your ultimate product is R, C, double bond O, and this OR dash, OR dash. Also, you need to understand one thing, that during this esterification, your carboxylic acid is losing the OH group, and your alcohol is losing the H plus. So that OH minus and this H plus will combine to give you H2O as byproduct, right? So please remember that esterification is a reaction of alcohol and acid, of course, where alcohol functions like a nucleophile, right? And on the carbonyl group of your carboxylic acid, you get your SN reaction. Apart from carboxylic acid, here I can also use acid chloride with alcohol. It will also give you ester, only the byproduct will change. In this case, it will be HCl. Instead of acid chloride, I can also use anhydride, right? So with anhydride also, it will give you ester. Again, the byproduct will change. So whether it is acid or acid derivative like acid chloride or anhydride with alcohol, all of them, they give ester, and that's why these reactions are called esterification reaction, right? So after esterification, the next important reaction of alcohol we have is SN reaction. Although the SN reactions of alcohol, especially these reactions, you must have seen in the haloalkanes chapter, right? Even if you see the one-shot video of haloalkanes, haloarenes that we have provided, so in that also I have discussed these reactions in very much detail, right? Why? Because alcohol, when it reacts with HX, so it follows SN1 mechanism. With PX3, PX5, it follows SN2 mechanism. With SOCl2, it follows SNI mechanism, but with SOCl2 pyridine, it follows SN2 mechanism. So these are SN reactions of alcohol, but in each cases, your mechanism is different, right? With alcohol HX, it follows SN1 mechanism. Sometimes we use anhydrous ZnCl2 catalyst here, especially if your alcohol is of lower degree, right? After this SN1 reaction, you will be getting Rx and your byproduct will be H2O, right? If you talk about alcohol with PX3, right? Again, it is SN reaction, more precisely SN2. In this case, you will be getting Rx plus byproduct will change. It will be H3PO3. And when you treat with PX3, one molecule of PX3 will react with 3 molecules of alcohol to give 3 molecules of alkyl halide with H3PO3 byproduct. When you treat alcohol with PX5, right? So again, it follows SN2 mechanism. In this case, you will be getting alkyl halide as your product, and the byproduct will be POX3 along with HX, And finally, if you talk about alcohol with SOCl2, so without pyridine, it follows SNI mechanism, right? In SNI mechanism, you will have retention. But when you use pyridine as catalyst, then it follows SN2 mechanism, and you know that in case of SN2, instead of retention, you will be having inversion of configuration. So in this case, again, you will get RCl, but the byproducts are SO2 and HCl. Remember, this is called Darjan's process, and this is one of the best method of preparation of alkyl chloride, because we get purest form of alkyl chloride here. right? So if you want mechanism of these reactions, you can refer to the haloalkanes, haloarenes video. There I have discussed each and every mechanism in detail, right? I have discussed SN1, right? In first case, this OH bond will break after protonation from this H plus. You will get a carbocation, and that X minus will attach with carbocation to give Rx, right? In this case, the oxygen part of alcohol will attack on this phosphorus. So one X minus will be released from this, and that X minus will do back attack to give you Rx. Same mechanism for PX3, right? But one thing we need to highlight here, that this particular reaction of alcohol with HX, right? This reaction is also treated like a test of alcohol, right? You call that Lucas test. You call that Lucas test, right? In Lucas test, we use HCl with anhydrous ZnCl2. So point is, because this follows SN1 mechanism, right? So the one in which you get more stable carbocation will react faster here. So that's why in the Lucas test, when your alcohol reacts with this Lucas reagent, right? So 3-degree alcohol, which can produce most stable carbocation, will react immediately, will give turbidity immediately, right? But if you take 2-degree alcohol, right? So 2-degree carbocation is less stable than 3-degree. So 2-degree carbocation, it can take 2-degree alcohol, it can take 3 to 5 minutes for the reaction. But 1-degree alcohol if you use, right? So 1-degree carbocation is very, very less stable. So it will not react without heating or without using anhydrous ZnCl2. So it requires heating. Under normal condition, it will not react, it will not produce turbidity, right? So according to the timing of the reaction, whether it is reacting immediately, whether it is taking up to 5 minutes, whether it is not at all reacting at normal condition, we can check, we can distinguish the degrees of alcohol. So Lucas test is used to find out what is the degree of your alcohol, whether it is 1 degree, whether it is 2 degree, whether it is 3 degree, right? One more thing, just for your simplicity, just to make it easier for you to remember, please remember, all of you, that whenever in your organic reaction you see HCl, PCl3, PCl5, right? PBr3, PBr5, SOCl2, SO2Cl2. So treat them like a halide donor. Treat them like a halide donor. Like HCl can give you Cl minus, PCl3 can give you Cl minus, PCl5 can give you Cl minus, PBr3 can give you Br minus, SOCl2, SO2Cl2 can give you Cl minus. So just for your understanding, right, remember like this, that these are halide donors, right? HX, PCl3, PCl5, PBr3, PBr5, right? Or SO2Cl2 or SOCl2. So that will make it easier for you to decide the product from the substrate, right? Now, after this SN reaction of alcohol, one very much important reaction we have for alcohol is dehydration. You know that dehydration is a kind of elimination reaction, right? For alkyl halide also we have elimination, but for alkyl halide we call that beta elimination or dehydrohalogenation. But for alcohol, right, the concept is similar. The concept is similar, but we call it dehydration because overall from alcohol, one water molecule is getting removed, right? So point is, if you take an alcohol and you treat that with some dehydrating agent, here the dehydrating agent that you can use, it can be concentrated H2SO4, it can be concentrated H3PO4, right? It can be even aluminium oxide, right? Or it can be even ZnCl2, right? So that can act as dehydrating agent. So when you do dehydration here, using these dehydrating agent, most common one is H2SO4. What happens to students? From the alpha carbon, OH group will be removed, and from the beta carbon, one hydrogen will be removed, and you will get a double bond. The product will be alkene here. The product will be alkene here, right? But if you focus on the mechanism, again, in this acid-base dehydration, acid-catalyzed dehydration reaction, we get carbocation as intermediate, right? So in the acid-catalyzed dehydration of alcohol, because we get carbocation intermediate, again rearrangements are possible in this, right? Overall, if you notice, so in this reaction, this OH group will be protonated by the H plus first. Later on that OH will be removed. A carbocation will be formed on the alpha carbon first, right? You need to check for the rearrangement whether your carbocation can become more stable by hydride, methyl shift or ring expansion. And finally, you will have deprotonation through hyperconjugation to give you the final product, that is alkene. Now, if you remember, when you talk about dehydrohalogenation of alkyl halide, so in that case, right, most of the time, the major product is decided by Sedzeff rule, right? Sedzeff rule. So in this case also, the major product is decided using the same Sedzeff rule. Right? So if you have more than one beta carbon from which hydrogen can be removed, right? If you get more than one product by dehydration, right? So more stable alkene will be the major product. That's the point of your Sedzeff rule, right? Let me tell you that with an example, right? Suppose if I take this alcohol, right? So in this alcohol, if you notice carefully, so this is your alpha carbon and these two are your beta carbons, right? When you do dehydration using concentrated H2SO4, so first this OH will be protonated by H plus, this bond will break, you will get a carbocation here, right? And hyperconjugation can occur from this beta 1 carbon as well as beta 2 carbon, right? So you can get two products here. One product will be like this, methyl. From beta 1, if you get deprotonation, so your product will be this. And from beta 2, if you get deprotonation, then your product will be this methyl group, double bond here. Now, out of these two, if you notice carefully, this alkene has 3 hyperconjugates from this, 2 hyperconjugates from this, and 2 hyperconjugates from this. So 3 plus 2 plus 2, total 7 hyperconjugates for the above alkene. And for this one hyperconjugate from here and 2 hyperconjugates from here. So this has only 3 hyperconjugate. So definitely here, the more stable alkene is the above one. So this will be your major product according to Sedzeff rule. So just remember one point, right? That during the dehydration of alcohol also, the major product is decided using the Sedzeff rule, right? So after dehydration, one of the most important reaction of alcohol is oxidation, because from this you get so many questions. And again, in the oxidation part, you have to learn, you have to understand some of the oxidizing agents in detail, right? First point is, when you try to oxidize alcohol, so there can be two type of oxidation. One is mild oxidation, partial oxidation. One is strong oxidation, right? When you do mild oxidation of alcohol, you can obtain aldehyde ketone. But when you do strong oxidation of your alcohol, you can obtain carboxylic acid. So for this, we need to use suitable reagent. First, if I talk about the mild or partial oxidation of alcohol. So mild or partial oxidation of alcohol can be done by PCC or PDC. I hope you remember PCC. It's a very famous, right? Pyridinium chlorochromate. So either you can use PCC or you can use anhydrous CrO3. So PCC and anhydrous CrO3 can do mild oxidation of your alcohol, right? That means what? If I take 1 degree alcohol, primary alcohol, and I treat that with PCC or anhydrous CrO3, so it will do mild oxidation. It will remove 1 hydrogen from this carbon, 1 hydrogen from this oxygen, and you will get a double bond between carbon oxygen. So with 1 degree, your product will be aldehyde, right? 1 hydrogen we are getting out from this carbon and 1 hydrogen is getting out from this oxygen. right? So we get a double bond between carbon oxygen. So from 1 degree alcohol and its oxidation, its mild oxidation, you obtain aldehyde. But instead of that, if I take 2 degree alcohol, if I take 2 degree alcohol, I use the same reagent, right? So in this case, again, these two hydrogens from carbon oxygen, it will be removed. Between carbon oxygen, you will get a double bond and your product will be ketone. Your product will be ketone. And I hope you remember from aldehyde ketone chapter that ketones are very difficult to get oxidized further. Ketones are difficult to get oxidized further. Now point is, after 1 degree, 2 degree, if you try to oxidize 3 degree, so oxidation of 3 degree alcohol is very, very difficult, right? With your mild oxidizing agent, even with your strong oxidizing agent, right? Under normal conditions, you cannot oxidize 3 degree alcohol. For 3 degree alcohol, you need drastic condition, very, very high temperature pressure. So under drastic condition, if you oxidize 3 degree alcohol, so ultimately that will also give you nothing but ketone, right? Now, after this mild oxidation, if I talk about strong oxidation, so strong oxidation of alcohol can be done by the very famous potassium permanganate, K2Cr2O7, or Jones reagent. You know Jones reagent, CrO3 with H2SO4, right? And even if you take hydrated CrO3, CrO3 with water, CrO3 with water. So that can also act as a strong oxidizing agent here. But the main thing is, when you do strong oxidation, you will see difference only in the primary alcohol. Point is, in the primary alcohol, if you notice, so on your alpha carbon, because you have 2 hydrogen, so here you will have 2-time oxidation, right? Initially, these 2 hydrogen will be removed to give you aldehyde, but later on, that aldehyde will be further oxidized, right, into carboxylic acid. Into carboxylic acid. So point is, if you take 1 degree alcohol and you do strong oxidation with any of these, so from 1 degree alcohol, you will be getting carboxylic acid after a strong oxidation. But if you take 2 degree alcohol, right, so for 2 degree alcohol, even by strong oxidation, you will be getting ketone only. Even by strong oxidation with any of these, you will be getting ketone only, because in 2 degree alcohol, on the alpha carbon, we have only one CH bond. So only this hydrogen can be removed during oxidation, right? So for 2 degree alcohol, we do not have any difference, right? So for 2 degree alcohol, whether I use mild or a strong oxidizing agent, I will be getting ketone. But for 1 degree alcohol, when I use a strong oxidizing agent, I will get acid. When I use a mild oxidizing agent, I will be getting aldehyde, right? One more point separately you can remember, and that is, of course, we are talking about oxidation of alcohol, but please keep in mind that this PCC, pyridinium chlorochromate, it cannot oxidize the carbon-carbon pi bonds. In your substrate, if you have this carbon-carbon double bond, triple bond, right? So they are not oxidized by PCC. Please remember that. Because people sometimes they can give it to you to confuse, right, in the questions, right? So for PCC, please remember that it will not oxidize the CC double bond. Let me explain that with an example. Suppose, students, if I take this substrate, okay, I will have to take alcohol, yeah. So if I take this substrate and I oxidize this with PCC, so point is, because you have a 2 degree alcohol here, so from your alpha carbon, 1 hydrogen, and from this oxygen, 1 hydrogen will be removed, right? So that 2 degree alcohol with PCC, it will oxidize into ketone, right? It will oxidize into ketone. But this CC double bond, it will remain as it is with PCC, because PCC cannot oxidize the carbon-carbon multiple bonds. So isn't it quite similar to that LiLH4 NaBH4, although LiLH4 NaBH4, they are reducing agents and PCC is oxidizing agent. But still in them one thing is common, that whether it is LiLH4 NaBH4 or PCC, they will not alter, they will not affect the CC multiple bonds, CC pi bonds. right? So after doing all the preparations and reactions of alcohol, now let's see that what type of questions do we get in our examination, right? Because that can be a checklist for us, right? That whether whatever topics we have discussed, isn't it sufficient or not, right? So whether it is sufficient or not, whatever content you have covered, so that can be checked by the PYQs or by solving questions. So let's do some questions from this preparation and reactions of alcohol, and you can take your pen, paper and brain, and along with me you can solve those questions. And if you want, anytime pause at the question, do it by your own, and later on match the answer with me, right? So the very first question we have is, okay, it's a conversion question. Let's see what it says. You can pause it, you can do it by your own, later on you can see the answer with me. So question is, the major product D formed in the following reaction sequence. Now we are starting with alcohol, CH3OH. Let me draw a structure for this. You know what? It is always important to draw the complete structure when you are doing reaction around the alpha beta carbon. Do not expand the whole structure, but at least around your alpha beta carbon you need to expand it to understand the reaction easily. So this is CH3OH. Now what we are doing, we are treating with SOCl2. Today only I told that remember SOCl2, PCl3, PCl5, HCl, they are like chloride donor, right? So if it can give chloride donor, even if I don't know the mechanism that whether it is following SNI, SN2, I can say like this, SOCl2 can give Cl minus. So that Cl minus will replace, of course, nucleophile. Here OH minus is the nucleophile. So after treating with SOCl2, I will get CH3Cl. And of course, if you talk about detail, then this reaction follows SNI mechanism. We have retention in that, right? Same side. Now, in the second step, we are treating this with KCN. Now this reaction, now it is from alkyl halide. When you have a alkyl chloride and you treat with KCN, so KCN can give you Cn minus nucleophile. So you can have SN2 reaction then. This C minus can attack here, chloride will go out. Your product will be methyl cyanide, CH3Cn. Again, Cn has this structure C triple bond N. So this is your B. Now what you are doing, you are treating it with sodium amalgam and ethanol. You know what? Sodium amalgam ethanol or metal alcohol or metal acid, they acts like reducing agent. Please remember, whenever you see metal with alcohol, metal with acid, so it can function as reducing agent. So when I reduce this C triple bond N, right, the pi bond will be removed and hydrogens will be added. So your C will be something like this. C is CH3. Now this nitrile, it will be reduced into CH2 single bond NH2. This is your C, CH3, CH2, NH2. Now what you are doing, you are treating it with NaNO2 HCl, which is nothing but nitrous acid indirectly, NaNO2 HCl, or it can be written as HNO2. And then we are doing hydration. So if you remember your amine chapter, so in your amine chapter, when you treat primary amine with nitrous acid, so initially it gives you azo compound. But if it is aromatic, it gives diazonium salt. But if it is not aromatic, it is simple open chain or simple cyclic ring, right? So that N2 plus becomes unstable. So with treatment with water, it gives you ultimately alcohol, right? So in this case, this NH2 part will be completely removed by this NaNO2 HCl and H2O, and you will be getting CH3, CH2, OH as your product, right? And when it is a aromatic compound, if you take aniline here, then it is called, if you remember, diazotization reaction, right? So in this case, our final product is ethanol, CH3CH2OH. Of course, answer will be C. But if you notice, this question carries concepts of different chapters, right? This concept was from alcohol chapter. This concept, this step was from alkyl halide chapter. This is again from amine chapter. This is from amine chapter. Right? In amine chapter, you talk about preparations of amine, and in the preparation of amine, you do reduction of cyanide into amine, right? So of course in this case the answer should be C, and yes it is. But point is, this question we got in the NEET 2024 examination. So now you can judge, now you can guess what type of questions we get from this alcohol chapter. Right? I'm not saying phenol ether because we have not seen phenol ether yet, right? We're gonna see this phenol ether after alcohol. So let's do few more problems. Can we do this one? Again, identify D in the following sequence. It's a very simple reaction if you notice. If you take CS3CH2OH, so P plus I2, indirectly it is PI3. Right? Because PI3 is not very much stable. PI3 is not stable. So we use P plus I2 to create that, right? And as soon as it is formed, right, it reacts with CS3CH2OH. So again, PX3, PCl3, PI3, it can act as halide donor. So from PI3 you will be getting I minus, right? SN2 mechanism. This OH will be removed, right? A will be CS3, CH2I. Now you are treating with Mg dry ether. So this is nothing but Grignard formation, right? So B will be CS3, CH2, Mgi, right? And for Grignard, you need to remember one thing, that this is always anion, this is always cation. Now you are treating this B with formaldehyde, HCHO, right? We saw that in the preparation of alcohol, that when we take formaldehyde, HC double bond OH, and if I treat this with Grignard reagent, CS3, CH2 minus, Mgi plus, so it will have nucleophilic addition reaction. This carbon will attack on this carbon, pi bond will break, and when you do protonation, so you will be getting alcohol here. So here the final product, it should look like this. This CH2, this will become single bond O. Initially you will have OMGI, but with protonation it will convert into OH, and this CH2, CH3 will attach. So in this case we are getting CS3, CH2, CH2OH. This is nothing but propanol or N-propyl alcohol. N-propyl means all the carbons, they are continuously attached with one another. So in this case, answer should be A, and it is A, right? So till now, these two questions that we have seen, in them the concepts were from the preparation and reaction both of alcohol. And this question again we got in the NEET 2024 examination. So you have done 2 PYQs, that is from 2024 exam. Now the next one is, can you do it by your own? Which one of the following alcohol reacts instantaneously with Lucas reagent, right? I told you, Lucas reagent is nothing but anhydrous ZnCl2 along with HCl. And this test tells you about the degree of alcohol, whether it is primary, secondary and tertiary. So the tertiary alcohol or 3-degree alcohol reacts faster. Now if you check the options, in the first option, the alpha carbon is, what's the degree? I think degree you can easily assign, right? The alpha carbon is attached with 2 more carbon. So here it is 2 degree. Here the alpha carbon is attached with only 1 carbon. So this is 1 degree. Here the alpha carbon is attached with 3 CH3, 3 carbon. So this is 3 degree. And in this case, the alpha carbon is attached with only 1 carbon. So 1 degree. So out of all the options, if you notice, in C option, we have 3-degree alcohol, we have tertiary alcohol. So that will react fast or fastest with the Lucas reagent. That will give you immediate turbidity, right? So in this case, of course, answer should be C, and yes, it is C. And again, this question we got in the NEET 2024 examination, right? Now, the next one, can you do it by your own now? Because these reagents are pretty much known to you now. The major products A and B formed in the following reaction sequence. Now, if you focus on the substrate, you have a alkyl group here, cyclic ring, methyl, alcohol. So OH is the main group here. We are treating with PBr3. So PBr3 will give Br minus. That Br minus will replace OH according to SN2 mechanism. So A will be something like this, CS3, and now instead of OH we have Br. Now we are treating with alcoholic KOH, reaction from alkyl halide chapter. You know that alcoholic KOH will do beta elimination reaction, right? So in this case, now this is your alpha carbon, and you have two beta carbons here, beta 1, beta 2, and both have hydrogen. So from beta 1, if you do elimination, your product will be this methyl double bond, and from beta 2, if you do elimination, your product will look like this. But you know that in normal eliminations, right, if it is not alkyl fluoride, if it is not bulky base, so in normal cases, we get ZZ product, right? So out of these two alkene, of course, the more stable alkene is this one. The more substituted alkene is this one. So this will be your major product, and they are asking for the major, right? So now if you check the options, we have to answer what is A, what is B. So this was your A. This was your A, right? This one is correct, not correct, not correct, correct. So two options are eliminated from this. Now we are left with 1 and 4. So now check the major product. In first case, this is your major. This is not correct. This is correct, right? So here, correct answer should be fourth one, right? This is your A, and this is your major product because it is more substituted alkene. So of course, in this case, our answer should be fourth. And yes, it is. And this question again we have from NEET 2024. So in NEET 2024, you can see that we have so many questions because we had re-examination in 2024, right? That's why we have more questions from NEET 2024. Now, can you do this one? It's a direct question for you. Pretty much direct question for you. Just a single step. Consider the following reaction and identify the product P. Okay. So if I consider this, we have an alcohol as substrate and HBr. You know very well that when alcohol is treated with halo acid, right, HCl, HBr, it follows SN1 mechanism. It follows SN1 mechanism. Now, I don't have to tell you what is SN1. You know it very well from your alkyl halide chapter. In SN1 mechanism, first of all, this OH will be protonated by H+, right? Later on, this CO bond will break, H2O will go out, and you will get a carbocation like this. This CH3, then this CH. Let me expand this structure. Then this CH3, then this carbon where you have your carbocation, and then the last CH3 like this. Now, one thing is always we have to focus on that in any reaction when we get carbocation, so we need to check for rearrangement. Now here if you notice, currently our carbocation is of 2 degree. Right side it is 1 degree carbon. So shifting the carbocation on the right hand side will not benefit you, will not increase the stability of carbocation. But the left side carbocation is already 3 degree. If I shift carbocation on left hand side, the stability of carbocation will increase. And here it can done by shifting this hydride. If I move my hydride here and cation here, so this is called hydride shift. So after hydride shift, your carbocation will become 3 degree. So automatically the stability of carbocation is increasing. So this will be a spontaneous process, right? So after hydride shift, this is the most stable carbocation. Now rearrangement is not possible in this. So at the end, ultimately the Br minus nucleophile, it will attack on the carbocation to give you the final product. Now if you see the options carefully, in our product, on the 3 degree carbon, we should have Br. So here it is on 1 degree, not correct. Here it is on 3 degree, correct. So that should be your answer. In the rest of option, here they have done elimination, not possible. Right, here they have attached on 2 degree carbon, not possible. So the major product is 2. Yeah, answer is 2. And this one we got in the NEET 2023. So now I think comfortably you can do the PYQs. And if you are able to do the PYQs, similar type of questions you can expect in your NEET examinations too. Right? Now, the next one. Can you do it a little bit quick, a little bit faster? Which among the following will be most readily dehydrated under acidic condition? Now, we know that dehydration is one of the major reactions of alcohol. And we have seen that during the acidic dehydration of alcohol, we get carbocation intermediate, right? So because during dehydration under acidic medium, we get carbocation intermediate. So point is, on the basis of stability of carbocation, we can decide its reactivity. Now, if you check all the options here, in the first case, you will get a carbocation on this carbon after removal of this OH, of course. In the second case, you will get carbocation here after removal of OH. In the third case, you will get your carbocation here, right? And in the fourth case, you will get a carbocation here. Now, if you notice carefully, in the first, second and fourth option, we have a nitro group. Nitro group is electron withdrawing group. Nitro group is a minus I group, and minus I group always decreases the stability of carbocation. So because in 1, 2, 4, we have NO2 attached, so NO2 will decrease the stability of carbocation. So the case in which we don't have any NO2 group, right, that will be the most reactive alcohol here, right? Although in this case we have another OH group here, and that OH group can act like a minus I group for this carbocation, but if you compare the strength, right, so NO2 has a very, very high minus I effect as compared to OH. So if I compare, definitely the third one will be the most reactive in the dehydration. Of course, it is the third one. But the main thing here is, you need to understand that during the acid catalyzed dehydration of alcohol, because we get carbocation intermediate, so we need to compare stability of carbocation to check reactivity, right? And no doubt we got this question again in NEET 2023. Now students, the next question we have is which of the following compounds can be used as antifreeze in automobile radiators? Basically, this is a question from alcohol, but again from the uses part, right? So if you know, right, the anti-freezing agent in our automobile radiators, right, it is very famous. It is nothing but glycol, ethylene glycol. So answer here, it should be officially, of course, A. And this question we got in the AIPMT 2012 examination, right? Now let's quickly see the next question, right? When glycerol is treated with excess of HI, so again we have a question now here from the reaction part of alcohol, and we saw that in common names, right, that when you say glycerol, so glycerol means you have 3 carbons, CH2, CH, CH2, and on each carbon you have a hydroxy group. So it's an example of a trihydric alcohol. So this is your glycerol. Now point is, when you treat this with excess of HI, right, so initially it will be similar to like the reaction of alcohol with HX, right? You know SN1 reaction. When alcohol reacts with HX, so that OH group is removed by the X group. So same thing will happen here, right? If you have a 3 OH group and if you take excess of HI, so one by one, these OH groups will be replaced by the iodide, right? And ultimately, you will get this product, CH2I, CHI, CH2I. But here we have a problem because iodine has a very, very large size. So the carbon iodine bond, right, it is not very much stable. And when you have multiple iodines adjacent to it, adjacent to one another, so from that automatically the carbon iodine bonds will break and I2 will be eliminated. So initially we got this triiodo compound, but now because carbon iodine bond is weak, right, so these 2I will be eliminated in the form of I2. And when that will be eliminated, you will get a double bond here. So it will be like CH2 double bond CH, CH2I, and one I2 is now out. Now point is, because HI is in excess and now we have a CC double bond, so on this CC double bond, again you will have Markovnikov addition, electrophilic addition of alkene, right? So on this double bond now, again HI will be added according to Markovnikov rule. The H plus ion will be added here on this carbon where we have more hydrogen, and iodide will be added here where we have less hydrogen. So after that electrophilic addition, now your product will be CH2 will become CH3. On this carbon, you will have another I, right? And this carbon already had an I. Now again, we have 2 adjacent iodines. So again, this will be removed in the form of I2. Right, and now you will be having CH3, CH, double bond, CH2, one I2 is out. but of course Hi was in excess. So one more time you will have electrophilic addition reaction, and now on this alkene, when you will be having electrophilic addition of Hi, so again according to Markovnikov rule, the H plus ion will be added here, iodine will be added here, and your final product, final stable product will be CS3 CHI CS3. So that will be the final product. Now you have only one iodine, right? So I2 can't be removed, and you don't have any double bond, so Hi can't be added. Now if you check the options, so this is nothing but if you do the IUPAC nomenclature like 1, 2, 3, so 3 carbon propane, and on the second carbon you have iodine, so it will be 2 iodopropane. 2 iodopropane, if you look at the options, it is in the A option. So of course in this case our final product will be 2 iodopropane, right? And this question, of course answer will be A. This question we got in the AIPMT 2010 examination, right? Now of course we will move into phenol, but before we move into phenol, I would like to add a point here which most of the time we forget to read, or you can say revise. You know what, students, when you talk about oxidation of alcohol, right? So no doubt you have oxidation of alcohol with PCC, PDC, right? Jones reagent, CrO3, right? KMnO4, K2Cr2O7. But we have a kind of oxidation, or more precisely you can say dehydrogenation of alcohol with copper. And sometimes we do get question from that. Like when you heat alcohol with copper at some 573 Kelvin temperature, right? So for different degrees of alcohol, you get different product, right? With the same reagent, copper and 573 Kelvin heat temperature, if I use 1 degree alcohol, let me write it R here in general. So with 1 degree alcohol, it will be quite similar to PCC, right? Mild oxidation, right? This OH, this hydrogen will go out, and from this carbon one H will go out, and CO in between you will have a double bond. So with 1 degree alcohol, you will get aldehyde. Similarly, if I use 2 degree alcohol, right? So in 2 degree alcohol, again these two hydrogens will be dehydrogenated. Your product will be RCR double bond O. So these two products, they looks like oxidation product, right? Especially the mild oxidation part, right? Where 1 degree alcohol oxidizes into aldehyde, and 2 degree alcohol oxidizes into ketone. But point is, 3 degree alcohol, they are very much difficult to oxidize. But in this reaction, if I use 3 degree alcohol, let me take an example here. Yeah. So because this is a kind of dehydrogenation reaction. So in this case, right, your 3 degree alcohol, instead of converting into ketone, right, it will convert into alkene. In this case, what will happen, right? This OH will be removed, and from this carbon, one hydrogen will be removed. So it is something like a dehydration reaction with copper heat. So with 3 degree alcohol, right, your product will be CH2 double bond C CS3 CS3. So with copper heat, you can say that 1 degree, 2 degree alcohols kind of they get oxidized into aldehyde ketone. But with 3 degree alcohol, your product becomes alkene, which is quite similar to the dehydration reaction. So my point is, reaction of alcohol with copper and a high temperature, right? It is nearly 300 degrees C or 573 Kelvin. This reaction is also important for you because you do get questions from this also, right? Sometimes in your examination. Now, after completing the alcohol part, the preparation and reactions of alcohol part, now let's go into the next part of the chapter, right? And next part is nothing but phenol, right? I hope the basic fundamental structure of phenol you all know very well. When I say phenol, that means I will have a benzene ring, right? And one of the hydrogen is substituted by the hydroxyl group, right? So this is the structure of your phenol. Now for phenol, when you talk about its preparation, so the very first preparation we have is from haloarenes, or you can say aryl halide, right? And it is again one of the substitution reaction. It is one of the SN reactions that we have. Like if I take haloarenes, like in your books you will find this, like chlorobenzene. And first thing is, for haloarenes, the SN reactions are difficult. You know that, you have seen that in your aryl halide chapter, right? Because we have partial double bond character here due to resonance. So because in case of aryl halides, the SN reactions are difficult, so we need high temperature to do SN reaction. So at high temperature like something similar to 623 Kelvin, and high pressure like 300 atm. So at this extreme condition, if I use aqueous NaOH, so now this OH minus nucleophile can attack on this carbon. For some time, both chlorine OH will be attached, and later on that chlorine will be leaving the benzene ring, and ultimately your product will be not phenol but sodium phenoxide, because this reaction is happening in the basic medium. So once your OH will attack, it will replace the chlorine. Suppose you got this phenol. But please remember that phenol is acidic in nature. Phenol can easily donate its H+. Phenol can react with bases. So because in this reaction we are preparing in basic medium, so once you obtained phenol, so that phenol will further react with NaOH, right? So it will lose its proton in basic medium. So ultimately here the product will be sodium phenoxide. Now if you want phenol, so further you need to do protonation. Once you do protonation, the metal part, the sodium ion part will be removed, and instead of Na+, you will have H+. And this method, if you know, it is also called as Dow's process. Dow's process of preparation of phenol, right? So that's how you can prepare phenol from haloarenes, right? Now, after haloarene, the next preparation method of phenol is from benzene sulfonic acid. It is very important, because many times I have seen in questions that conversion of benzene sulfonic acid into phenol, they asked in the sequential questions, right? Those types of questions where from A you get B, from B you get C, right? So in those questions I have seen this part, right? So point is, what is benzene sulfonic acid, students? Benzene sulfonic acid is benzene having SO3H group. Now if you want how you can prepare this, how you can prepare benzene sulfonic acid, so you may have seen that in your hydrocarbon chapter, right? In hydrocarbon chapter, right, to prepare this benzene sulfonic acid, what we do, we take pure benzene and we do sulfonation of this, right? Sulfonation of benzene is nothing but electrophilic substitution reaction. So with benzene, if I add oleum, which is basically H2SO4 plus SO3, or sometimes we write it like H2S2O7 also, right? So with benzene, if I put oleum, I can get my benzene sulfonic acid. But now the point is, with benzene sulfonic acid, if you add simply NaOH, right, you will have desulfonation reaction. Desulfonation means from here, this SO3H group will be removed by this OH minus nucleophile, kind of SN reaction again, right? And in this case, again, you will be getting sodium phenoxide, but later on, if you do protonation, you will get what? Phenol. So desulfonation of benzene sulfonic acid can be done by simply heating it with NaOH, right? Now, after benzene sulfonic acid, the next preparation is from disonium salt. I think disonium salt is everywhere, right? It is very important for your organic chemistry, right? Most of the aromatic compounds you can prepare from benzene disonium salt. So I hope that you know very well the structure of benzene disonium salt. Benzene disonium salt is benzene having N2 plus and Cl minus ion, right? If you want the detailed structure of this, then it is something like benzene N triple bond N, right, positive charge. This is the structure of your azo group. So in this benzene disonium salt, if you want to get, right, phenol, you have to do simple treatment with water. Simply you treat this with water, right? What will happen? In this structure, if you notice, benzene N2 plus, N2 already it is a very good leaving group. So N2 has tendency to go out. It just want to go out from this benzene structure. Now, when I treat with water, so water, you know that it can act as a nucleophile. So this water molecule, it will simply help the N2 to go out, right? It can attack on this carbon, right? This CN bond will break, electron pair will go on to the nitrogen. So this N2 will go out and this oxygen will attach with your benzene. And later on, you know that whenever H2O attacks, right? So because oxygen gets positive charge, so you will be having a deprotonation at the end. But ultimately, just by treatment with water, just by hydrolysis, right, of disonium salt, you can obtain what? You can obtain phenol. So these are simple methods of preparation of phenol, whether it is directly from haloarine, whether it is from the desulfonation of benzene sulfonic acid, or whether it is simple hydrolysis of disonium salt. From these three directly you can get what? Phenol. But the next method, which is from cumene, it is very much important for us. And there are multiple reasons for that, right? Two reasons are, one, from cumene, when you prepare phenol, so this is our industrial method of preparation. This is our industrial method of preparation. Means on the larger scale, if you want to phenol, we use this, right? On larger scale, if you want to prepare phenol, we use cumene process. And secondly, this is a reaction in which, if you notice, you will have phenyl shift. You will have phenyl shift. Phenyl shift. So I will tell you with mechanism that where you have phenyl shift in this. But if you talk about overall the reaction, the cumene process. So in cumene process, of course, our substrate is cumene, and cumene is nothing but isopropyl benzene. This is the structure of your cumene, benzene. And with benzene, you have an isopropyl group, which looks like this: C, H, CS3, CS3. So point is, when you take cumene and you oxidize it with oxygen, O2, simply, right? So these two oxygen atoms, they will go in between the CH bond, right? It will create this kind of intermediate, benzene, C, OOH. We have a peroxy linkage here, and the methyl part will be as it is. Now let me tell you first what is happening here. See, you take benzene, and here we have a isopropyl group. Now, when you add oxygen here, so oxygen is a oxidizing agent, so it will have tendency to gain electron. And in your substrate, if you notice, the richest carbon in terms of electron is this one. Why? Because this carbon has a CH bond. So a carbon having CH bond, it can easily oxidize, it can easily donate electron. And secondly, it is attached with benzene. So whenever this carbon will have a deficiency of electron, right, it can gain electron from benzene through resonance. And third point, this carbon is 3 degree. It is attached with 3 different carbons. So you know that 3 degree carbons, they are rich in electron, then 2 degree, then 1 degree. So this carbon has the highest tendency to get oxidized, right, or to donate electron. And it can donate electron from the CH bond. So what it will do? It will donate its electron of CH bond to this oxygen, right? Again, to maintain the valency, right? One of the pi bond will shift on this oxygen, right? And this H plus, finally it will be added on this carbon. So you will have this kind of structure: carbon single bonded with oxygen, oxygen single bonded with oxygen, and then oxygen bonded with hydrogen. This is what we are getting. And here we have a peroxy linkage. You know that oxygen-oxygen single bond is called as peroxy linkage. So we get initially this intermediate. But when this is treated with water or acid water, right? Of course, this part, especially the peroxy linkage, it is unstable, so it will break and ultimately it will give you this product. It will give you phenol, and here the byproduct is acetone. Here the byproduct is acetone, CS3CO, CS3. Now, when you convert this into this, so in this part we have phenyl shifting. How? So let's see that with the mechanism. See, initially we got this intermediate, and in this we have this peroxy linkage. Now we know that peroxy linkage is unstable, so definitely it will break. And suppose we are having a heterolytic fission here. So when this bond will break, right, this electron will be taken by this oxygen because cation is more stable on this oxygen because it is having inductive effect from carbon, right? So after fission of this peroxy linkage, this side you have OH minus and this side you have C, phenyl group, CS3, this one, CS3, this one, and O plus. Now you know that even in case of carbocation, you have rearrangements, right, to increase the stability of positive charge. Now here, when your positive charge is on oxygen, so as compared to that, if your positive charge is on carbon, then it will be more stable, right? So this positive charge will shift on this carbon, and how this will happen? By the phenyl shift. This phenyl group will move on to this oxygen and this positive charge will come onto this carbon. And after rearrangement, now your structure will be something like this. This carbon having 2CS3 group, right? Oxygen having the benzene ring, and here we have a positive charge, right? So by this shifting, we obtain the most stable cation. If you want, you can do other shiftings, like instead of phenyl, you can shift methyl. But with that, you won't get the most stable cation. We always get most stable cation here by shifting the phenyl group, right? And once you get that, once you get this phenyl group shifted onto the oxygen, right? For some time, this OH minus, which were getting released here due to fission of O bond, you can attach here just for neutrality. But later on, right, in water, this part will break completely from here, right? This part will be converted into phenol. Of course, this bond will move on to oxygen, right? And this OH part, right? Let me draw it a little bit in a better way, especially that OH part. Yeah, once you attach this OH here, so this bond will move on to oxygen forming phenoxide, and this OH bond will move between carbon oxygen. So this will give you CS3C double bond O CS3, and this H plus will attach here to give you phenol, right? Sometimes we get isotope type of problems here, right? Just for that phenyl shifting part. Like suppose in this structure, if this is O16 and this is O18. So in your final phenol, right, you will have O16 here, right? And how to know that we are having O16? Because we are having a phenyl shift here. Phenyl shift here, right? You can't get O18 here. Done. So this process, cumene process, is important for us mainly for two things. First, it is a industrial method of preparation of phenol, and second, we have somewhere phenyl shift in this process. And we get so many questions from this, right? So you should have the knowledge of this complete conversion of cumene, right, into this intermediate and finally into acetone and phenol, right? So these are the preparation methods you have for your phenol, correct? Now, immediately just after the preparation, now for phenol also, you will talk about some of the important properties of phenol. Like one of the important properties is phenol is having acidic nature. Although I have told you already that phenol is acidic in nature, but we saw this point in alcohol also, right? We saw that alcohol is having also acidic character. But if you compare that out of alcohol and phenol, out of alcohol and phenol, which one is more acidic, right? Then definitely phenol will be more acidic. Phenol will be more acidic as compared to alcohol. Why? The answer lies in the stability of conjugate base, right? For a normal alcohol, its conjugate base means after removing this H plus, the conjugate base will be alkoxide, Ro minus. But for phenol, after removing this H plus, the conjugate base that you get is a phenoxide ion, right? So you know very well that in phenoxide ion, we have a resonance effect, right? This negative charge can be delocalized into this benzene ring due to resonance. This negative charge can delocalize on these three carbons, ortho para carbons, right? So due to resonance, this conjugate base has more stability, and if your conjugate base is more stable, then your corresponding acid is more acidic. So always phenol is more acidic than your alcohol. Now second point is, you saw the reaction of alcohol with metal. So just like alcohol, even your phenol can react with pure metals like sodium or magnesium. Phenol can also react with pure metals like sodium, magnesium, aluminium, right? And it can give what? Phenoxide. Along with phenoxide, just like alcohol, you will be getting hydrogen gas here. But there is a difference. You saw that apart from methanol, rest of the alcohol, they do not react with bases like aqueous NaOH, aqueous KOH. But phenol will react with bases, right? Phenol will react with aqueous NaOH to give you sodium phenoxide, or with KOH to give you potassium phenoxide, right? One more point, sometimes you will be getting question here about the comparison of acidic strength of phenol, right? So you know very well that when you add some electron donating group, so electron donating group will decrease the acidic strength, and when you add electron withdrawing group to your phenol, so that will increase the acidic strength. And answer again lies in the stability of conjugate base, right? For phenol, the conjugate base will be phenoxide, so that phenoxide can be stabilized by electron withdrawing group. So that's why its corresponding acid will be more acidic, right? And that phenoxide will be destabilized by the electron donating group. So that's why its corresponding acid will be less acidic. So you will be getting questions about comparison of acidic strength of phenol, right, on the basis of which electron donating group is attached to which electron withdrawing group is attached, right? So this is all about the acidic nature of phenol. Now, coming back to its reaction part, in the phenol, almost every reaction is electrophilic substitution reaction, right? But some of the electrophilic substitution reactions, right, it is very common, like alkylation, acylation, halogenation, nitration, sulfonation, correct? So almost most of the reactions of phenol, they are electrophilic substitution reaction, but some of them we will be discussing under this electrophilic aromatic substitution reaction. Although we never perform Friedel-Crafts alkylation acylation for phenol, because you know that phenol, right, it can directly combine with your AlCl3 catalyst. So we do not perform alkylation acylation of phenol, but we do perform the rest of the EAS reaction like halogenation and nitration. So in the EAS part for phenol, these two are the important reactions for you. One is nitration, one is bromination. Point is, when you do bromination, please focus. When you do bromination, I hope you know that during the bromination reaction, the electrophile is Br plus, right? And during bromination, you take phenol, and your reagent will be, of course, Br2. But there is a problem. What problem? With respect to benzene, OH will act as activating group. OH will increase the electron density of your benzene ring. Also, OH is ortho para directing group, right? So now because OH activates your ring, so there is a chance of poly substitution. there is a chance of poly substitution. So you will see two type of ES reaction here. One will be poly substitution, means in your phenol, whatever ortho-para positions are there, on all those positions, your Br plus electrophile will be attached. Here also, para position also, and this ortho position also. This is called poly substitution. And another reaction you can have in which you will be having only mono substitution. Mono substitution means in a phenol, only one Br electrophile will be attached. So of course, you will be getting ortho product, you will be getting para product, but out of ortho para, always para is major if you don't have intramolecular hydrogen bond. So point is, in the bromination part of phenol, we have two type of reaction, poly substitution and mono substitution. Now we control this by medium, right? If you want to do poly substitution, you need more fission of this Br2, right? And more fission of Br2 into Br plus Br minus can be done in, right, ionic medium like water, right? And if you want mono substitution, you want less number of Br plus, you want less fission of Br2 into Br plus Br minus. So that can be obtained by using non-ionic medium, non-polar medium like a carbon disulfide. So here in the bromination part, we control mono substitution, poly substitution by medium. If I use non-polar medium like carbon disulfide, I will have mono substitution. If I use polar medium like water, I will have poly substitution. So please keep that in your mind. And the same point is there in your nitration reaction also. For your phenol, when you perform nitration, so again there are two possibilities. I hope you know that in case of nitration, you're attacking nucleophile. In case of nitration, you're attacking nucleophile, electrophile, not nucleophile, sorry. You're attacking electrophile is NO2 plus, right? But here with phenol, when I use HNO3, HNO3 will give you NO2 plus electrophile. So I can get this OH, NO2, 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 means poly substituted product. And I can also get this OH, NO2 and OH, NO2, means mono substituted product. Now in case of nitration, right, we control this mono substitution and poly substitution by the concentration of HNO3. Students, if you want poly substitution, means you want more NO2 plus electrophile. And to get more and more NO2 plus electrophile, what you need to take a concentrated HNO3. But if you want to limit the nitration, right, if you want to do mono substitution, you want less number of NO2 plus per molecule of your substrate. So in that case, you will be using dilute HNO3. So point is, in case of nitration, the mono substitution and poly substitution is controlled by the concentration of HNO3. Dilute will give you mono substituted product, orthopara, and concentrated will give you poly substituted product, right? It is called as 2,4,6 trinitrophenol, and it is very famous. It is also known as picric acid, if you know. This compound is called as picric acid, one of the highly acidic compounds, because it has 3 electron withdrawing groups, right? So after these two ES reaction, that means nitration and bromination, and in your examination, you will be always getting question from these two, bromination and nitration. So after these two ES reaction, now for phenol, we have some of the name reactions, right? And again, we have two name reactions here. One is called Kolbe's, one is called Reimer-Tiemann. And from those two, out of those two, Kolbe's, Reimer-Tiemann, at least one you get in your NEET examination every year, either Kolbe's or Reimer-Tiemann, right? And one more thing. Even your Kolbe's and Reimer-Tiemann reaction is a type of electrophilic substitution reaction. The only difference is here we are using different electrophile, right? In case of Kolbe's reaction, your electrophile will be CO2, carbon dioxide, right? In case of Reimer-Tiemann, your electrophile will be dichlorocarbene. So let's see these reactions one by one. In Kolbe's reaction, what you do, you take phenol, right? You use basic medium, NaOH. So NaOH, what it will do, it will deprotonate your phenol and it will convert phenol into phenoxide ion. So point is, as compared to your OH group, O minus is a better activating group. O minus have better tendency to donate electron to benzene as compared to OH group, right? Once you got this phenoxide ion, now you treat this with your electrophile CO2, right? When you treat this with CO2, right, and then you do protonation, of course, by passing it with acidic water, right, it will finally give you this compound, OH and C double bond OOH. It is called as salicylic acid. Salicylic acid. I hope you people know the mechanism of ES reaction because we started ES reaction from the hydrocarbon chapter itself, right? Like in this case, how this phenoxide ion will react with your CO2. It's very easy. You have your benzene ring which contains 3 pi bond. This O minus acting as a electron activating group, and this is your electrophile CO2, right? So electrophile will grab electron from your benzene ring, right? Or your benzene ring will share its pi bond with CO2, right? So to maintain valency, one of the pi bond of CO bond will go into oxygen, right? And you will get a cation here as intermediate, something like this. These 2 pi bonds will be as it is. Here you will get a cation attached with O minus, so O minus can stabilize that cation. And now here you have CO minus double bond O. So this is the first step, your ES reaction. Electrophile will be added on the pi bond of benzene. And the second step of ES reaction is always hyperconjugation. On the carbon where CO2 has been added, on the same carbon you have a CH bond. So that CH bond now, it will move towards this carbocation through hyperconjugation effect, right? So again your double bond will be created through hyperconjugation and this H plus, right, will go into the medium. And later on when you do acidification, so these O minus, they will grab the H plus to give you the salicylic acid. So point is, even the Kolbe's reaction which gives you salicylic acid is a type of electrophilic aromatic substitution reaction in which your electrophile is CO2, in which your electrophile is CO2. Now, just like Kolbe's reaction, we have another reaction which is called Reimer-Tiemann reaction. This reaction is also carried out in basic medium just to increase the reactivity. You take your phenol, you treat that with base like NaOH, convert this into phenoxide ion. Now here what you do, you treat this first with chloroform. So base is already there in the medium, so I can say chloroform and base. And then again you do acidification, right? So after these 2 steps, in this case, you will be getting salicylaldehyde. You will be getting salicylaldehyde. Correct? And even this is a ES reaction, but the main difference here is, in Kolbe's reaction, your electrophile is CO2, but in this reaction, in Reimer-Tiemann reaction, your electrophile is dichlorocarbene. Yes, carbene, very rare intermediate, right? Dichlorocarbene looks like this, carbon having 2 Cl bonds and an electron pair. So of course, it is an electrophile only, but this electrophile is nothing but dichlorocarbene. And this dichlorocarbene here, we generate using these 2, CHCl3 and NaOH. What happens? This CHCl3, when it is treated with NaOH, so I hope you people know about beta elimination, right? Beta elimination is the one where from your alpha carbon halogen is removed and from the beta carbon hydrogen is removed, right? So it is like a polyhalogen compound, right? Not like, it is a polyhalogen compound. So in this case, when you add base, so instead of beta elimination, because you have only 1 carbon here, So in this case, you will be having alpha elimination. From the alpha carbon itself, one chlorine will be removed as chloride ion and one hydrogen will be removed as H plus. So by alpha elimination with NaOH, right, of this chloroform, Cl minus and H plus will go out. So you are left with what? You are left with carbon and two chlorine bonds. This electron pair, it will be taken by your chlorine, and this electron pair, it will remain on the carbon. And when this bond will break, carbon will get plus charge. When this bond will break, carbon will get minus charge. So net charge will be 0. So this carbon is neutral now. And this is nothing but your electrophile here, which I said dichlorocarbene. Now further, if you talk about how this reacts with your phenoxide ion, same concept, right? You know ES mechanism very well. Same step will be repeated, just like your Kolbe's reaction and the rest of the ES reaction. This pi bond will be shared by the electrophile. Here you will get a carbocation, right? Later on you will have a hyperconjugation. So ultimately you will obtain this product, right? Phenoxide and this carbon CH, Cl, Cl. Right, after attachment with benzene, this carbon will gain a negative charge. So this lone pair will be shared by the H plus, right? So you will get this CHCl2. And when you do acidification, right, so these chlorines will be removed by the OH group. Later on, it will convert into carbonyl, right? So ultimately, you get salicylaldehyde in this. But the main thing is, whether it is Reimer-Tiemann, whether it is Kolbe's, whether it is bromination, nitration, all are electrophilic substitution reaction. That's the point. That's how you need to memorize this. The only difference in each cases, your electrophile is different. In case of Reimer-Tiemann, your electrophile is CCl2, carbene. In case of Kolbe's reaction, your electrophile is CO2. In case of nitration, your electrophile is NO2 plus. In case of bromination, your electrophile is Br plus. Right? And these are the major reactions of your phenol. Electrophilic aromatic substitution reaction. But apart from these electrophilic substitution reactions, right, you have a few more reactions, right? One is reaction with zinc. You can say that reaction of phenol with zinc is a kind of reduction reaction, right? What happens when you take phenol, right? And when you add zinc here, so this zinc will simply absorb the oxygen, right? Just for fun, you can say like this, zinc in its valence shell, it has 2 electrons, right? And oxygen, for the oxygen atom in atomic form, it has 6 electrons in the valence, and to complete octet, oxygen always needs 2 electrons. And oxygen is a greedy atom, right? So point is, when this oxygen will see that zinc has an electron pair, right? It will leave these 2 hydrogen. So you will feel that your oxygen is becoming selfish here. It is breaking the bond to take electron of zinc, right? So oxygen atom will take electron of zinc. It will convert into zinc oxide. And this hydrogen and this carbon of benzene, they will attach to give you simple benzene. So you can say that it is one of the preparation of benzene you have, right? From phenol with zinc dust directly into benzene. Not only that, suppose that in your benzene, if you have more than one hydroxyl group, 2, 3, right? So if you have more than one hydroxyl group, still if you add zinc dust, still you will be getting benzene as your product. So zinc can remove multiple oxygen from this, right? So you can say that it is a reduction of phenol with zinc dust. Sometimes we do get question from this, not because it's a reaction of phenol, but mostly because it is a preparation method. It is one of the preparation method of benzene from phenol, right? Now, after reduction, one more reaction we have for phenol, which is called oxidation. Although it is very difficult to oxidize phenol, but at high temperature, if I use strong oxidizing agents like K2Cr2O7 or KMnO4 at high temperature, phenol can be oxidized into benzoquinone. benzoquinone looks like this. So you can note it down. Sometimes you will be getting questions from these two reactions also, apart from electrophilic substitution, right? Whether it is oxidation, right, of phenol into benzoquinone, or whether it is reduction by zinc dust, conversion of phenol into benzene, right? So this is all about your phenol and its preparation and reactions. So of course you will you will notice that the content in phenol is a little bit lesser as compared to alcohol. The number of reactions in the preparation and reaction of phenol is lesser than the alcohol, right? But probability of getting question from alcohol and phenol, it is quite equal, 50-50%. Sometimes we get question from alcohol, sometimes we get from phenol, and sometimes we get question from both. One question from the alcohol part, one question from the phenol part, right? So now let's see some of the questions from this preparation of phenol and reactions of phenol. Take your pen, paper and brain, right? Along with me, you also need to do these questions with yourself, right? For each question, pause the video. Try to do it by your own first, right? And then play the video. Later on, you can check the answer, detailed answer and the solution. So the first question we have here is, it looks from which one of the following reaction sequence is incorrect method to prepare phenol? So I think this is a question from the preparation part of phenol, right? And we have 4 options and we have to see which one is incorrect. So out of these 4, at least 3 of them can be used to prepare phenol, right? So let's check one by one. First one is aniline. Aniline, you know that it is benzene, NH2. When you treat aniline with NaNO2HCl, right, nitrous acid, it is called a diazotization reaction. So aniline with NaNO2HCl, it will produce nothing but disonium salt. In amine chapter, we have this reaction, right? And when you treat that with water, right, when you heat that with water, we saw that it's called hydrolysis of disonium salt. N2 will be removed and you will be directly getting phenol. So first method is okay. First method can be used to prepare phenol. Now the second method is cumene. We saw that cumene process is industrial process, right? Cumene, CH3 whole twice CH, treated with O2. So when you treat that with O2, you get this, this kind of intermediate, benzene, COOH, and CH3 whole twice. And when you do hydrolysis in acidic medium, you get phenol as your product, and byproduct is acetone, CH3CO, CH3. So even the second one is a preparation method of phenol. Now if you check the third one, so we have haloarine here, chlorobenzene, treated with NaOH. Okay, so they have written STP condition. Now you know that I told you that because we have a double bond characteristic in the haloarine between halogen and carbon, so its SN reaction is difficult. So under STP condition, you can't do this reaction. You need high temperature, at least 623 Kelvin. So third method cannot be used to prepare phenol. That will be your answer. Now if you check the last one, so benzene with oleum will give you benzene sulfonic acid, and benzene sulfonic acid with NaOH, it will do desulfonation and it will give you finally phenol. So first, second, fourth can be used to prepare phenol, but third can't, and this is what they are asking, which is incorrect. So third is incorrect. Your answer will be third one, right? Third is your answer. And this question again we got very recently in the NEET 2022 examination. Now with this, let's move ahead. Let us see the next question from the phenol part. Can you do this? We have a matching problem here. Pause the video, do it by your own. Later on, you can match your answer. So match the reagents, list 1, list 2 from phenol. Okay, I think benzoquinone, if you read the options in the list, it looks like it's a question from the properties part, reaction part. So benzoquinone That was the last reaction that I told you, right? We get by the oxidation of phenol. Oxidation by strong oxidizing agent like Na2Cr2O7 H2SO4. So D here, it will match with first, right? Benzene. This we saw when phenol is treated with zinc dust, we get benzene, right? So phenol when treated with zinc dust, we get benzene. So C will match with 2. Aqueous NaOH, chloroform gives you dichlorocarbene, and dichlorocarbene was the intermediate in Reimer-Tiemann reaction, right? And in the Reimer-Tiemann reaction, our product was salicylaldehyde. So here, B will match with third. So automatically, NaOH CO2, CO2 was the electrophile in your Kolbe's reaction, and in Kolbe's reaction, our product was salicylic acid. So A will match with nothing but fourth, right? So A4, B3, C2, D1. That should be our matching. A4, B3, C2, D1. And that's your answer, right? A4, B3, C2, D1. Correct? And this matching problem, basically a problem from the reactions of phenol, we got again in the NEET 2022 examination. So now you can guess what type of problem you will be getting in the phenol part, whether it is preparation, whether it is reaction, right? Let's see a few more questions. Can you do this one? You don't have to solve. It's just a logical question for you. Statement based. Statement 1. Again pause it. Do it by your own. Again, always. So the acidic strength of mono-substituted nitrophenol is higher than phenol because of electron withdrawing nitro group. Of course, I told you, right? In your phenol, when you attach electron withdrawing group, so that will increase the acidic strength. And when you attach electron donating group, so that will decrease the acidic strength. So of course here, statement 1 will be absolutely correct, right? Nitrophenol will be more acidic than normal phenol, right? Now, the second is orthonitrophenol, metanitrophenol, paranitrophenol will have same acidic strength as they have one nitro group. No. When you attach electron withdrawing group, so their positions also matter, right? Especially the meta position, because most of the time when you attach electron withdrawing group which can show minus R effect, which can withdraw electron through resonance, so minus R effect will be shown at ortho para position. But the same group, when you attach that at meta position, it starts showing minus I effect. You don't have minus R effect then. So if I compare paranitrophenol and metanitrophenol, these two only. So with respect to OH, when it is at para position, this NO2 will have minus R effect because it will participate in the resonance. But with OH, if it is at meta position, it can't show minus R, it will show minus I effect, because during resonance of this OH group, due to this OH group, electron density will be at this position, and this position. So only at these positions you can have minus R effect. At meta, you won't have minus R effect, you will have minus I effect. You know that minus R is better than minus I. So I can definitely say that paranitrophenol is more acidic than metanitrophenol. So they can't have the same acidic strength. So definitely here, statement 2 will be incorrect, right? Now check out the options. Both statement 1, 2 correct, no. Both statement 1, 2 incorrect, no. Statement 1 correct, statement 2 incorrect, yes. Answer should be C here. And of course, that's your answer. And again, this question was in NEET 2022 itself. Now, the next question. Can you do it? Can you do it, all of you? This question we got in the NEET 2019 examination, and it looks a direct question from the preparation, right? If you recall, this is nothing but isopropyl benzene or cumene, right? You oxidize cumene, you get some intermediate, you do hydrolysis, you get this product. So they are asking, what is your intermediate here? Very easy, right? You know that during this oxidation, between this CH bond, we get that peroxy linkage, right? And if you look at the options 1, 2, 3, 4, so in the third option, you have that, right? between this carbon hydrogen, you have a peroxy linkage. So of course in this case answer should be third, and that's your answer. So sometimes we get direct question from the intermediates, right? Now the next question, can you do it? Again, it's a question from the preparation part itself. Identify the major products PQR. Okay, so here the first step is benzene is your substrate, alkyl chloride is your reagent, and AlCl3 is your catalyst. So this is nothing but Friedel-Crafts alkylation reaction. But I hope you know very well that in Friedel-Crafts alkylation we have a problem of rearrangement, right? You know that in Friedel-Crafts reaction, this alkyl chloride and AlCl3, they will interact. This chloride will be absorbed by the AlCl3, right? And on this carbon, you get carbocation. So initially, your carbocation will be like this: CH3, CH2, CH2 plus. But you know very well that in any reaction, when we get carbocation as intermediate, so there is a chance of rearrangement. And in this case, you will have rearrangement definitely. There will be hydride shift, right? And then your carbocation will be like this: CH3, CH plus CH3. So now it became 2 degree from 1 degree. You know that 2 degree carbocation is always more stable than 1 degree carbocation. So it is nothing but Friedel-Crafts alkylation, but with rearrangement. So after rearrangement, you get this carbocation, and now your benzene, again with same mechanism it will react. You know that pi bond will be shared by carbocation, you will get a positive charge here, hyperconjugation, right? And ultimately your product P will be benzene attached with this carbon. This carbon has a hydrogen and 2 methyl group. So can you figure it out? What is this? This is nothing but cumene, right? Cumene, isopropyl benzene. And now this cumene, when you treat with O2, it is nothing but cumene process, right? O2 will form peroxy linkage here, COOH, and Q and R will be nothing but phenol and acetone. Phenol and acetone. So we have identified very easily that here P is isopropyl benzene, Q and R, right? One of them is phenol, one of them is acetone. Now if you check the options, first one is incorrect. You cannot have N-propyl benzene. Second is also incorrect. You cannot have N-propyl benzene. Third is correct here. Fourth is correct here. Now the next one, you won't get benzaldehyde, right? Of course, already it was cancelled. You can get phenol, of course. You can get phenol, of course. So this is right. Okay, here we have byproduct as alcohol, and here we have acetone. So of course, acetone is the right answer. So correct answer here should be fourth one. And I can say that it's a direct question of cumene process, right? Conversion of isopropyl benzene into phenol. The only thing they have added here is how we can prepare isopropyl benzene using propyl chloride with AlCl3 by Friedel-Crafts alkylation reaction. And this question, students, we got in the NEET 2018 examination. Correct? Now, can you do this one quickly? It's a direct question. And just now I have told you while I was explaining the reaction. So in the reaction, the electrophile involved is, so this reaction, if you try to identify phenol, chloroform, base, it is nothing but Reimer-Tiemann reaction, right? Or your Reimer-Tiemann reaction, whatever you say. So in Reimer-Tiemann reaction, we saw that chloroform base, right? They do alpha elimination and they produce this Cl2 carbene. So the intermediate or the electrophile here will be dichlorocarbene, right? It can't be carbocation, right? Dichlorocarbene. I hope you remember that dichlorocarbene in your syllabus of organic chemistry, I think it is there in 2 reactions and both of them are name reaction. One is this Reimer-Tiemann reaction and one more reaction is there in which your intermediate is dichlorocarbene. It is carbylamine reaction or isocyanide test in your amine chapter. So in those 2 reactions, Reimer-Tiemann and isocyanide test, you have the intermediate as or electrophile as dichlorocarbene. And in both the cases, to generate dichlorocarbene, you will notice that we use chloroform and base. Correct? So of course in this case answer should be fourth, and that is your answer. And again this question we got in the NEET 2018 examination, right? Now, can you answer this one? Not from the preparation part, not from the reaction part. This time we have a question from the comparison of acidic strength, but I think you will do it, all of you. Which one is the most acidic compound? If you see the options carefully, in first case we have a simple phenol. In second case we have phenol with one NO2 group at para position, so it can show minus R effect. In third case we have a phenol with 3 NO2 at ortho para, so all of them can show minus R effect. And here we have methyl group. Methyl acts as electron donating group. It can show plus hyperconjugation or plus inductive effect. So point is, minus R effect will increase the acidic strength, plus H or plus I effect will decrease the acidic strength. So here C and B will be more acidic than A and D. And out of B and C, if you notice, right? Out of B and C, if you notice, C has more number of electron withdrawing group. So definitely in this case, most acidic will be C. We can write down the order here. Most acidic will be C, then it will be B. Then out of A and D, because D has electron donating group, so A. And then at the end you have D. So order of acidic strength here will be C, B, A, D. But they are not asking this. They are asking that which one is most acidic. So most acidic will be of course C, option C. Yeah, C is your answer. And this question again we got in the NEET 2017 examination, right? Now, the next question we have is, if you read carefully, reaction of phenol with chloroform, fine. Chloroform means CHCl3. You know that very well. In presence of dilute sodium hydroxide. So, you know that chloroform, sodium hydroxide, it can give you dichlorocarbene. Finally introduces which one of the following functional group on phenol, right? So, you know very well about your Reimer-Tiemann reaction, right? In Reimer-Tiemann reaction of phenol, we use chloroform and NaOH as a reagent that generates CCl2 carbene, and ultimately in the product you get salicylaldehyde. So, it introduces aldehyde group, you can say, right, in your phenol. So, of course, in this case, answer should be C. Yes, it is. And again, students, this question we got in the NEET 2015 examination, right? So, with this, now, I hope we are done with the questions from the phenol part, and you have understood from what part we get questions very often in the preparation of phenol and in the reactions of phenol. So, now, after alcohol, the first part, phenol, the second part. Now, let's talk about the third part of this chapter, which is ether. But again, you will notice that as compared to alcohol, we have lesser reactions in phenol. And again, as compared to phenol, we have much less reactions in the ether part, right? But I hope as a functional group, you know ether. Ether is a bidirectional functional group like this. Oxygen attached with alkyl group on two sides. But it can be of two types, right? It can be symmetrical, it can be unsymmetrical. And it's very easy to guess what is the meaning of symmetrical and unsymmetrical ether. Symmetrical means around your oxygen, when you have same alkyl groups, methyl, methyl, ethyl, ethyl, propyl, propyl, like this, right? And unsymmetrical means around your ether group, when you have different alkyl groups, right? Methyl, ethyl, ethyl, propyl, right? Phenyl, methyl. So when you have different alkyl groups around your ether group, around your oxygen, so that is called unsymmetrical ether. And when same alkyl groups are attached around the oxygen atom, so then it is called symmetrical ether. And I hope that for ether, nomenclature part you know very well, right? Ether is named as alkoxyalkane. Ether is named as alkoxyalkane, right? The alkyl group with highest number of carbon in the chain is written as alkane, and the other alkyl group along with oxygen written as alkoxy, right? So nomenclature I think you know from your GOC chapter also. So now let's quickly start with the preparation of ether, right? And when you talk about preparation of ether, So very first method of preparation of ether is from alcohol. Students, in this session only, we have talked about, right, dehydration of alcohol using acid, right? So when you do dehydration of alcohol, right, so you obtain what? Alkene. But that is a kind of strong dehydration, you can say, right? If you do partial dehydration of alcohol, so by partial dehydration of alcohol, you can obtain what? Ether. And we have a difference in temperature. Please remember that if possible. Like when you perform the dehydration of alcohol at 140 degrees Celsius, which is basically 413 Kelvin. So at this temperature, if you do dehydration of alcohol, you can obtain ether. But if your temperature is 30 degree more, like nearly 170 degrees Celsius or 443 Kelvin. So at this temperature, you can obtain your alkene. So how we obtain alkene by the dehydration of alcohol, we saw that in the reactions of alcohol. So in that reaction, now you can add that that reaction happens at 170 degrees Celsius. But when you try to prepare ether from alcohol, so that reaction you can perform at 140 degrees Celsius. What happens when you take alcohol, right? So two alcohol molecules, right, at again 140 degrees Celsius or 413 Kelvin temperature, right? They will have partial dehydration. Partial dehydration means from one of the alcohol H plus will go out and from the other alcohol OH minus will go out, right? And this RO minus, this R plus, they will combine to give you ROR, right? And if you talk about this according to its mechanism, so kind of you can say it is an example of SN reaction. In this reaction, what happens? One of the alcohol molecule, it will act like an nucleophile, and the other molecule, it will act like a substrate. So here what happens? This nucleophile will attack on the positive center, right, carbon, and it will replace the OH minus nucleophile. So overall you can say that of course it is partial dehydration of alcohol, but in terms of SN reaction, if you want to see, you can say that here OH minus nucleophile is getting replaced by the RO or alkoxide nucleophile, right? And by the replacement of OH with OR, we are obtaining what? Ether, correct? So this is a method, one of the easiest method to prepare ether from your alcohol, right? In the same method, with the same method, you can also prepare, if you want, cyclic ether. You can also prepare cyclic ether from this. Like if you take dihydric alcohol like this, right? And here if you do partial dehydration, right? So again, one of the OH, its carbon will act as positive center, and one of the OH here, it will function like a nucleophile. It will attack here, right? Partial dehydration, again you can say this OH minus this H plus will go out, and you can obtain cyclic ether from the same, right? Cyclic ether, they are also called as oxyranes, correct? So whether it is open chain or cyclic, both type of ether can be obtained by this partial dehydration of alcohol, right? Now, apart from partial dehydration of alcohol, the next method is much more important for us, and we get a question from this very often. It is name reaction, Williamson synthesis, and this reaction you must have seen in your haloalkanes chapter, because of course it's a preparation of ether. It's a name reaction, but it is a reaction of alkyl halide. It is a reaction of alkyl halide. In Williamson synthesis, what you do, you take alkyl halide, you treat that by sodium alkoxide. You know that alkoxide is a very good nucleophile, strong nucleophile. So it will attack on the alpha carbon. It will go through SN2 reaction, SN2 mechanism, and finally it will produce ether group, right? So it's an example of SN2 reaction of alkyl halide, where this RO minus or alkoxide nucleophile is attacking and this halide is going out. So RO minus is replacing the X minus nucleophile. But one thing here is very important. You know that in SN2 reaction, reactivity depends on steric hindrance, right? And for alkyl halide, we have lowest steric hindrance when it is 0 degree or 1 degree alkyl halide. So in Williamson synthesis, we always use 0 degree, 1 degree alkyl halide to obtain ether. If I use 2 degree or 3 degree alkyl halide instead of 0 degree, 1 degree, so in that case, instead of ether, you will end up getting alkene. Why? Because in case of 2 degree, 3 degree alkyl halide, when I use Ro minus, right? So this Ro minus, instead of nucleophile, moreover, it will act as a base. So it will cause beta elimination. So in this case, substitution, elimination, both will happen, but elimination will dominate. And because elimination will dominate, so 2 degree, 3 degree alkyl halide with your sodium alkoxide will produce alkene more as compared to ether. So that's a point in your Williamson synthesis reaction. What? That in Williamson synthesis, we prefer 0 degree or 1 degree alkyl halide, right? If I use 2 degree, 3 degree alkyl halide, then instead of ether, the major product will be alkene. The major product will be alkene. So these two are the main preparation method of your ether, right? And not only this, using this method, you can also prepare your cyclic ether again. Like if you have a compound in which on one carbon you have halogen and on one carbon you have oxide or OH group, right? So you can have intramolecular SN reaction to get ether. So from the same method, you can obtain open chain ether and cyclic ether, right? And these two are the major preparation methods of your ether: Williamson synthesis and partial dehydration of ether. Correct? Now, let me give you few more examples in this Williamson synthesis part. Suppose if I take this CS3Br, it's a 0 degree alkyl halide. I treat with some CH3, CH2, ONA, sodium ethoxide. So because it is 0 degree, it will easily produce ether through SN2 reaction, right? Br will be replaced by CH3, CH2O, and here your product will be CH3, CH2, O, CH3, means ethyl methyl ether, right? But suppose instead of 0 degree, 1 degree, if I use this, if I use 3 degree alkyl halide with the same reagent, that means CH3, CH2, ONA. So now in this case, because my alkyl halide is 3 degree, right? So now elimination will dominate. Now this ethoxide will act as a base, right? So it will remove a proton from the beta carbon. From alpha carbon, bromine will go out and it will have beta elimination reaction. So your major product will be CH2 double bond C, CS3 and CS3. So please keep that in mind. 0 degree, 1 degree alkyl halide with sodium alkoxide will give you ether, but 2 degree, 3 degree alkyl halide with sodium alkoxide will give you alkene instead of ether, right? Now, immediately after the preparation of ether, right, we can talk about its physical property, in which if you compare the boiling point, so ether, right, they are polar in nature. Of course, they can't form hydrogen bond in between, right? Ether molecules, two ether molecules, they can't have intermolecular hydrogen bond in between them, but they are polar in nature because of CO bond. So because ether is polar in nature, what happens as compared to normal hydrocarbons, right, whether it is alkane, alkene or alkyne, ethers have more boiling point. But of similar molecular mass, if you compare ether's boiling point with corresponding alcohol, like you have one alcohol, we have one ether, and they have similar molar mass. So for similar molar mass, if I have ether on one side and if I have alcohol on other side, right? So because we have to discuss both these two in this chapter itself, so that's why we are comparing these two. So as compared to alcohol ether, in comparison of alcohol ether, alcohol will have more boiling point as compared to ether, right? Because you know alcohol has intermolecular hydrogen bonding, but ether will have more boiling point as compared to the hydrocarbons like alkane, alkene, alkyne of comparable molar mass. I hope this point you can easily remember in your mind. So let's move into the main reaction of ether. Believe me, for ether, this is the only reaction which is very much important to you. From this only you get so many questions in the examination. Reaction of ether with halo acid. Of course, it is an example of SN reaction again, but point is, normally what happens, either a reaction follows SN1 mechanism, like if you talk about reaction of alcohol with HX, so that follows SN1 mechanism, or your reaction follows SN2 mechanism, like if you react alcohol with PCl3, PCl5, that follows SN2 mechanism, right? But in this case, when you react ether with HX, halo acid, both SN1, SN2 is possible. So you will have to decide, right, by observing the structure of ether, that whether it will follow SN1 mechanism or SN2 mechanism. But overall, both mechanism is possible here, right? Also, if I have a symmetrical ether, if I take this ROR and I react this with HX, so for symmetrical ether, you won't have any doubt regarding the product. If I have symmetrical ether, both side I have the same alkyl group. So one of the alkyl group will combine with X to give you alkyl halide, and the other alkoxide part will combine with H plus to give you alcohol. So overall point is ether after reaction with HX, it will produce alcohol and alkyl halide. But when you have unsymmetrical ether, then you will have to decide which alkyl group will form alkyl halide and which alkyl group will form alcohol. And for that, right, decision making, you need to have understanding of deciding SN1 and SN2. Believe me, it is very easy. Just focus here. See, if I take this unsymmetrical ether, CH3O, CH2, CH3, and I reacted this with HCl, let's say. So what will happen in this reaction? First thing is, as soon as you mix ether with HCl, whether it is SN1, whether it is SN2, doesn't matter. First point is, it will get protonated, right? Your ether molecule, I am talking about the mechanism now, right? Your ether molecule has oxygen, oxygen has the lone pair, HCl will ionize to give you H plus. So first thing will be happening here is, oxygen will be protonated and you will get this intermediate, CH3, O. O will be attached with a hydrogen, a lone pair. O will have positive charge, and now CH2, CH3. Now from here, the main deciding factor will come. See, when your O has positive charge, so what oxygen will try to do? It will try to attract these carbon-oxygen bonds. It will try to attract these electrons of these bonds. But point is, if you can get a stable carbocation, so then your bond will break, a carbocation will be formed, right? And if you are getting a carbocation, that means it will follow SN1 mechanism. But if you can't get a stable carbocation from this, right, then the CO bond will not break. Instead of that, the nucleophile, the X minus nucleophile will come, it will attack, and after attack of nucleophile, this CO bond will break. So that is nothing but SN2 mechanism. So now here you have to see carefully that around your oxygen, you will have two carbon, this carbon, this carbon. Are you getting a stable carbocation? When I say stable carbocation, that means I will have to see either 3 degree or resonance stabilized carbocation. That's it. If I can get a 3 degree carbocation, if I can get a carbocation which is resonance stabilized, right, then carbocation will be formed and it will follow SN1 mechanism. But if I can't get this, if I am getting a simple 0 degree, 1 degree, 2 degree carbocation, not a special one, right? So in that case, because that 1 degree, 2 degree carbocation is not stable, so that carbocation will not be formed, and then your mechanism will be SN2. So in this case, in this example, if you notice, this carbon is a simple 0 degree carbon and this carbon is a simple 1 degree carbon. If I break this bond, here if I create carbocation, so that will be 1 degree carbocation, not stable. If I break this bond and I create carbocation here, so again 0 degree carbocation is not stable. So from any side, I am not able to get any stable carbocation, 3 degree or resonance stabilized. That means in this case, we can't form carbocation. So that means in this case, it will follow SN2 mechanism. It will follow SN2 mechanism. And in SN2 reaction, you know very well that the upcoming nucleophile prefers that carbon which has less steric hindrance. So this is 0 degree, this is 1 degree. Of course, hindrance is less here. So this X minus will attack here. Now this bond will break. The electrons will go at oxygen. You will get CS3X. Means in this case, you will get CS3Cl. And along with that, you will get CS3CH2OH. So I hope you have understood my point, what I am trying to say. Attach the proton on the oxygen, right, from both the side. From any side, if you are getting a stable cation like 3 degree or resonance stabilized, then you do the reaction by SN1 mechanism. But if you can't get 3 degree or resonance stabilized carbocation, you will have to follow the SN2 mechanism, right? Let me give you few more examples here. So this was example of SN2, right? Suppose I take this C, CS3, 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 O, CS3 with some HX. Now here, you know in your mind that this oxygen will be protonated. But now think like this. If I break this bond, this CO bond, I will get carbocation here, which is a 0 degree carbocation, not at all stable. If I break this bond, right, here I can get carbocation, which is a 3 degree carbocation. 3 degree carbocation is stable, right? So in this case, from this carbon, I can get 3 degree carbocation. If I can get that stable carbocation, it will follow SN1 mechanism. Now, you know very well what is SN1 mechanism. In SN1 mechanism, first this bond will break, you will get cation. This X minus will be added on cation. So, this cation and X minus will combine to give you CS3, 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 tert butyl halide, and this CS3O minus will be separated. Later on, it will take that H plus to produce methanol. So in the same ether with same reagent HX, in the previous reaction, we had SN2 mechanism because this was 0 degree, 1 degree, and we were not getting stable cation, so it followed SN2 mechanism, right? But with the same open chain ether, with the same reagent, here we got SN1 mechanism because here from the left hand side, we were getting a stable carbocation. So now I think you have understood how to decide SN1 and SN2 cases in your ether with HX reaction, right? Let me give you a few more examples. If I have this, can you decide by your own whether it will follow SN1 or SN2 mechanism? Just look around your oxygen. With this oxygen on the right hand side, you have this carbon which is 1 degree, right? So from 1 degree, you can't get stable carbocation. Left hand side, you have 2 degree. Even 2 degree can't be giving you stable carbocation here. So neither from the right hand side nor from the left hand side, we are getting stable carbocation. That means what? We can't have SN1 reaction. We can't create carbocation here. So if it is not SN1, it will be SN2. And now again in SN2, this X minus will attack on a less hindered carbon, which is 1 degree. So X minus will attack here. Later on, this bond will break here, and you will be getting CS3CH2X along with CS3CH3O minus. Right? So when I will be solving some of the questions from this, you will get much better understanding. But I think you have understood, right, that from either side of the ether, from the either alkyl group, if I am getting a 3 degree or resonance stabilized carbocation, so I can do SN1 reaction. If I am not getting 3 degree or resonance stabilized carbocation from either side, I am simply getting 0 degree, 1 degree, 2 degree carbocation. So their carbocation cannot be created. So there you need to follow the SN2 mechanism, right? And you know very well how SN1, SN2 reaction happens. In SN1, first bond will break, cation will be created, and with cation, the nucleophile will attach. In SN2, first bond will not be, right, break. First the bond will not break. First the nucleophile will attack, and later on that CO bond will break. Correct? So this is the most important reaction of ether you have, student. Reaction of ether with HX, right? Now, In the second part, especially if you talk about the aromatic ether, so in the aromatic ether part, we have electrophilic substitution reactions. And when it comes to electrophilic substitution reaction, you know very well that those 5 reactions are common, right? Friedel-Crafts alkylation, Friedel-Crafts acylation, sulfonation, nitration, halogenation. So those 5 reactions will be here for your ether, aromatic ether, in the electrophilic substitution reaction. I think we don't need to do this one by one, right? If I take this type of aromatic ether, so you need to understand that here with benzene, the OCS3 group will act as electron activating group, and it is ortho-para directing, right? So whatever electrophile I will give, it will attach at ortho-para position, and para will be the major product here. So if I do what? Chlorination. Right, in chlorination we use Cl2, that will generate Cl+. So Cl+ will be added at either ortho position or para position, right? And again, if you don't have intramolecular hydrogen bonding, then para will be major, right? Similarly, if I do nitration is done by using HNO3, H2SO4. So HNO3, H2SO4 will generate NO2 plus electrophile that can attach at ortho para position again, and major will be para. This is major, and this is your minor product, right? If you do Friedel-Crafts alkylation, right, using some RCl and AlCl3. So again, in Friedel-Crafts, there is a possibility of rearrangement. Take that in your mind, always keep that in your mind. But if there is no rearrangement, right, or if there is arrangement, in both the cases you will be having a carbocation. So that carbocation will attach at para position and again at ortho position, but still para will be the major product, right? In the same way, you can talk about sulfonation. Treat this with oleum, right? You will get SO3H group at ortho para position. And acylation, in that case you will be getting acyl group at ortho and para position, but para will be major, right? So electrophilic substitution is very common, right? Till now you have seen that for benzene, for haloarine, for phenol, and now for aromatic ether, correct? So now after doing the preparation and reactions of ether, I think it's time to discuss some of the questions from the ether part and what kind of question we get in the NEET examination from this ether part. So can you do this by your own, all of you? I hope you can. Just pause the video, read the question, and try to do it by your own, all of you. Question is, consider the following reaction. So we have ether here, aromatic, right, and with halo acid. So you have to decide whether it is SN1 or SN2. Now if you check carefully, around this oxygen we have this carbon, right? So on this carbon, we can never create carbocation because positive charge on the phenyl group is highly unstable. But on this carbon, if I create a positive charge, it can be resonance stabilized. So that means what? On this carbon here, I can get a resonance stabilized carbocation. So carbocation can be formed in this. And if carbocation can be formed, can be stable, so automatically it will follow what? SN1 mechanism. Now do SN1 mechanism. In SN1 mechanism, what will happen? This bond will break first. Electrons will be taken by the oxygen atom, right? And you will get a benzyl carbocation, right? On other side, you will have phenoxide ion, right? So benzyl carbocation will gain the I minus to give benzene CH2I, and phenoxide will gain the H plus ion to give you phenol. So the product A and B, if you notice, one of them will be benzyl iodide and one of them will be phenol. First option, not at all related with the product. Second also not possible. Third also not possible. Fourth one, right? Can you see this? A is benzyl iodide and B is phenol. So that's your answer. Fourth one. Now, point is why we are saying that it is following SN1 mechanism, because in this ether, on the left hand side, we are getting resonance stabilized carbocation. So that's why it is following what? SN1 mechanism. And of course, the answer will be fourth one. And this question is very recent. We got it in NEET 2023 examination. So I think now you are comfortable in deciding SN1, SN2 for ether reaction with HI. Can we do few more from the ether part? Again, same. Again, same. Can you see this? If I take anisole, so anisole is this one, aromatic ether, benzene with OCS3. Again, reaction with HI. I told you that the reaction of ether with HX is the most important one. From that only you will be getting question every time. So if I take anisole and I treat with HI, so again I will have to decide. So on this carbon, forming a cation is impossible. On this carbon, we can get 0 degree carbocation, which is not at all stable, right? So neither we are getting 3 degree nor we are getting a resonance stabilized carbocation from any side. So in this case, SN1 is not possible. That means it will follow what? SN2 mechanism. And if it is SN2, so this bond will not break first. First, this I minus will attack. And I think less hindrance is there on this 0 degree carbon. So I minus will attack here. Then this bond will shift here. O minus will grab the H plus. So your products will be phenol. And along with that, you can say CS3I. One more thing, in this reaction, instead of doing SN2, SN1, because it is aromatic, so for aromatic, you can say like this also. We have a partial double bond character here due to resonance. So automatically this bond will not break. Always this bond will break, and that will give you CS3I and phenol. So now if you check the options, right? So phenol and CS3I is present in the fourth option. So here answer should be fourth one, and the mechanism of this reaction was SN2, not SN1. And this we got in the NEET 2020 examination, right? Now, can you do this again? Again same. Again reaction of ether with halo acid. This time we have a phenyl methyl ether. I think it's the same question, right? So they do repeat questions in the NEET exam also. So this is your phenyl methyl ether. If you treat that with HI, just now I said that it will follow SN2 mechanism. You will be getting phenol and methyl iodide. So phenol will be the answer. Of course, phenol will be the answer B, right? So you got this in NEET 2017. So if you notice, same question we got in the NEET 2017 exam, and same question we got in the NEET 2020 exam. Why? Because for ether, in the reaction part, the main reaction is reaction of ether with HX. So obviously they will be asking question from that part only, right? The other part was electrophilic aromatic substitution reaction of ether, right? Of course, in this case, the answer was phenol. Now, can you do this one by your own, all of you? It's a kind of a conversion question we have. So, we have an alcohol here, NaH. NaH can give you hydride, H minus. And I think it's quite obvious that if I have H minus, so it will not attach with anion. H minus will attach with a cation itself, right? And from alcohol, you can get H plus ion. So this H minus will combine with H plus, right, to give you H2. And that O minus will be with Na plus to give you that alkoxide. So they have already said that we have alkoxide here. Now, this alkoxide is reacting with methyl iodide, means alkyl halide, and we are having SN2 reaction. So we are getting this ether. So, okay, they are asking the name of this reaction. So we have seen that in the preparation, right, students? When alkyl halide is attacked by sodium alkoxide, right, to prepare ether, it is called Williamson ether synthesis or Williamson synthesis simply, right? So it cannot be alcohol formation, it cannot be dehydration reaction, it cannot be Williamson alcohol synthesis, it is Williamson ether synthesis reaction, right? So they directly asked the name of the reaction, right? and this question was asked in the NEET 2016 exam. Means if you remember what is Williamson synthesis, you can answer this question, right? And of course the answer is D, that is Williamson ether synthesis reaction. Now, can you do this one? Among the following sets of reaction, which one produces anisole? So anisole is that one, the aromatic ether we had, right? Phenyl methyl ether. So we have to check from which case we can obtain this product. So one by one, let's see. If I have ethanol with Grignard, in these two, you can notice that you don't have any benzene or phenyl ring. So automatically, if you don't have a benzene ring in this, you can't produce this. So A is eliminated just by looking at the formula. Now if you check the next one, C6H5OH, you treat that by NaOH. So these two, right, will deprotonate the phenol to give sodium phenoxide. Right? Now if you treat that by CS3I, methyl iodide, of course it will be Williamson synthesis reaction, right? So here the answer will be second one only. B should be the answer. Yes, B is your answer. And if you check the rest of the options, C6H5OH, if you treat with FeCl3, so it will form a coordination compound. Here C6H5OH can act as ligand, directly binds with Fe3 plus cation. And this is your toluene. Toluene with CS3COAlCl3, it will give you Friedel-Crafts acylation reaction, right? So it can't produce anisole. So the only correct option here is B. And again, this question we got, students, in the AIPMT 2014 examination, right? Now, one more question from the ether, but again from the same reaction of ether with HX. Can you do this now by your own? I hope you can. Surely you can. Definitely you can. Among the following ether, which one will produce methyl alcohol on treatment with hot HI? So one by one, let us see. In the first case, around your oxygen, this is 0 degree, this is 2 degree, right? So from any side, we cannot get stable carbocation, so we cannot have SN1 reaction. So we can have only SN2 reaction on this ether. And if it is SN2, the I minus will attack on less hindered carbon, which is this one, and this bond will break. So ultimately, I will be getting methyl iodide and this alcohol, right? Isobutyl alcohol. And they are asking for methyl alcohol. So first can't be your answer. In the second case, around your oxygen, this is 0 degree, this is 3 degree. So in this case, from this side, 3 degree, we can get stable carbocation. So this will follow SN1 mechanism. So in SN1, this bond will break first. Here you will get a carbocation and here you will get a negative charge. So this part will combine with H plus to give you methanol or methyl alcohol. So second will be the answer here, right? And in the next part, again, you can see this is 0 degree, this is 1 degree. It will follow SN2 mechanism. So I minus will attack here. You will be getting methyl iodide. Same for the fourth one. So in the first case, third case, fourth case, you obtain methyl iodide because it is following SN2 mechanism. But in the second case, you will get methanol, and here it is following what? SN1 mechanism. So second will be your answer. And this question we got, right, when NEET started in the year 2013. Right? So now I think you are pretty much comfortable in doing the reaction of ether with halo acid. Now, we have done the alcohol, we have done the phenol, we have done the ether part, right? But in the alcohol, there are few alcohols which are important to you. And sometimes we get direct questions, especially the identification type of problem from that. So you need to focus on those one or two alcohols, right? Common alcohols. One of them is methanol. You know the formula of methanol, it is CS3OH, right? But point is, methanol is also called as wood spirit because initially it used to produced by the destructive distillation of wood, right? Nowadays, we do not use that. We do not create that by destructive distillation of wood. Now we create that by hydrogenation of carbon monoxide in the presence of zinc oxide or chromium oxide, right? And of course, methanol is colorless But please remember that methanol or wood spirit is highly poisonous in nature. Methanol is poisonous. You cannot intake that, right? And after methanol, the second most important alcohol you have is of course ethanol, right? In wines and all we use ethanol, but its conventional way, the conventional way to prepare ethanol is by fermentation of sugar, right? In which sugar molecule in the presence of invertase enzyme, it breaks into glucose and fructose, and those glucose fructose again by zymase they are converted into ethanol, right? And again, just like methanol, ethanol is also colorless, and the major use of ethanol was, right, as a solvent, right? Ethanol is used as a solvent, especially in the paint industries, right? And because you know that people misuses ethanol, right? People drinks that ethanol. So to denature it, so to make it undrinkable, what we do, we add some poisonous substance like copper sulfate or pyridine to make it denatured. And when your ethanol contains copper sulfate or pyridine or any poisonous substance, then it is called as denatured alcohol. So I think at least you should have an idea regarding your methanol and ethanol, right? Now students, we have done this chapter thoroughly, alcohol, right, phenol and ether, and I want you to revise this in the same fashion. First you focus on alcohol, then phenol and then ether, right? In alcohols, whatever preparations, reactions are there. In phenol, whatever reaction preparations are there. And in ether, you have very less preparation and reactions. In the preparation part of ether, you have mainly Williamson synthesis. In the reaction part, you have mainly reaction with HX, right? In phenol, you have Kolbe's reaction, Reimer-Tiemann reaction, the bromination reaction, the nitration reactions. So those are important. And for phenol, the preparation of phenol by cumene process or hydrolysis of disonium salt, they are important. And for alcohol, it's oxidation with PCC, Jones reagent, KMnO4, K2Cr2O7, reaction of alcohol with copper heat, right? So those reactions are important, right? And I have already told you that in organic it is very important to make a list of your reagents. So in this chapter also, whatever reagents you saw, whether it is PCC, whether it is PCl3, whether it is SOCl2, whether it is ZnCl2. So for each reagent, you should write down what is the function of that particular reagent or catalyst. So that will help you to remember the points of organic chemistry for a longer period of time, right? And of course, what will be your homework from my side? It's only one thing, right? If you have watched this video completely, right? So you are now done with your alcohol, phenol, ether, but still, right, you have to do much task, right, in the solving the questions, right? So solve as much questions as you can, because of course, this is a one-shot video. So I try to discuss only those questions, right, which can cover my concepts, right? So some of the concepts I try to cover in the content part. Some of the questions I try to cover in the question part, right? So you need to do more questions, right? And for that we are providing the DPPs. In the video description you are getting the DPPs. On the PW app also you can get the DPPs. So download PW app, right? And that's all from my side in this video. Thank you so much. I will meet with you in the next one-shot video. Till then, bye-bye, over and out.